Once again, good morning, everyone. We will be starting the event shortly, but for those who have arrived, can you please fill up the entry form that will be sent in the chat right now? This will be for attendance taking and so that we can ensure that you are here. Okay, once again, very good morning to everyone here. So if you haven't done so, you can take your attendance by using the entry form in the chat room. But for now, we shall proceed on with the schedule for today.
Okay, so from 8:20 to 8:40, you guys will be having your first keynote presentation by ByteDance and Panasonic. Then from 8:45 to 9:45, you guys will have Introduction to Machine Learning Part 2. And then from 9:45 to 10:45, you guys will be working on your AI win petition. And then you have another workshop, which is face recognition with Python Part 2 from 10:45 to 12:45.
After a 1-hour lunch break, you have the next workshop, which is Music with AI by Diamond High School for another 2 hours. Then it'll be a 40-minute workshop, again by Diamond High School, on Evolutionary AI Part 1. And then from then on, you'll be given even more time to start on your, to continue with your submission. And for today, the submission will be whatever prototype you have on hand by 5:45. Even if you're not done, you just have to submit to us so that we can get a progress check. For yesterday's 2359 submission, we have said that we'll give you a feedback by 8:30, but we have decided to push it towards 9:40 because we have to benchmark it against the judges from AI Singapore, and so that we can make it the more fair and accurate.
So you guys already seen this table yesterday. So yesterday you've already pitched your idea. So if you thought that you didn't have enough time or you didn't do so well yesterday, it's okay because day 2 and day 3 you still have so many much points to get. So today will be progress check, which is another 400 points. And the maximum points you guys can get is 3,800. So I hope you guys will strive for that.
All right. For yesterday's submission, I heard that there was a couple of teams who did not submit. Please remember that the submissions are worth 400 points, so it is a lot. Well, it's not a lot of points, but it's quite significant. Anyway, for those of you who have any problem during the AI win petition, please remember to use the ticketing conference channel in Discord. Now we'll be moving on to the first keynote, which is going to be from Zheming and Rui En, who are interns. Okay, Zheming is an intern at TikTok/ByteDance, which is an app that most of us will have. And Rui En is an intern at Panasonic R&D. Both of them are former Diamond High School students, and however, today they are not able to join us, so they have kindly sent us a pre-recorded keynote for us to enjoy together. So now we shall watch the video together. If there is any audio or any video issues, please let us know in the chat so we can fix it as soon as possible.
Hello everyone, I'm Zheming, and today with Rui En, we'll be sharing on why you should do machine learning. So as I mentioned, I'm Zheming, and I'm currently a CS major and undergraduate researcher at Georgia Tech, and I used to be a H2 computing student at Diamond High.
Okay, hi guys, I'm Rui En. So I'm an aspiring ISTD student and an undergrad researcher at SUTD. So like before entering SUTD, I was a software engineer at Wiz Mobility, which is a startup that made Singapore's first outdoor delivery robot.
To get started and in order to share more about the applications of machine learning, we are going to show you some of the more interesting use cases for machine learning. So one example actually is the neural style transfer. And for this one, we're actually using TensorFlow, which is an in-browser example. So the idea of neural style transfer is that we will have a style image and a content image. So for the content image would be modified to adopt a style from the style image. I think let's show you an example. So for example, in this case, we will, let's say, so we have the images of the cats fighting, and maybe we want to use the style image of the screen. So the model would modify the image such that the original image of the cats fighting now adopts the style of the screen. Or we can choose another content image, for example, the image of Brad Pitt here, and we can use the screen as our style image, and similarly, it would adopt a similar style as well. So this is actually really interesting because we are able to use different content, we are able to modify different content images to adopt new styles easily. Yeah, and another example that is pretty interesting is, for example, using the MediaPipe library. So the MediaPipe library actually integrates different machine learning models, computer vision specifically. So in this example, we are using the hand pose detection, which detects hand key points. So the hand key points are actually points on your hand, for example, denoting the joints or the tips of your fingers, so that you are able to localize the position of your hand as well as where the different joints are. So using the MediaPipe library, actually we built this fun little code that is able to detect when your hand is closed like a fist, and that's when it creates the balls, and you are able to manipulate the balls as well when your hands are closed. So like this, we're able to move the balls, and if we open our hands, it doesn't affect the balls.
Right.
Yeah.
Yeah, pretty darn cool. Right, okay, so that's not the two examples you see are examples of supervised learning. So what we have to do is we provide the ground truth and then the model learns. So this example we have over here, the multi-agent hide and seek, is an example of reinforcement learning. So here reinforcement learning is applied on a hide and seek game. So like for most games, the AI like traditionally is quite primitive. So like normally like you hard code some kind of logic for the AI to follow. But then like with reinforcement learning, like the agents learn these strategies and policies like by themselves. Yeah. So the idea is that multiple agents and have many instances of the game with multiple agents pitting themselves against one another. Yeah, so like over here you can see there's two different factions. Not really factions. Okay, two different sides. Yeah, so there's the blue color agents. The blue color agents are the hiders. So their goal is to manipulate the environment before the seeking starts. And then like the red color agents you see are the seekers. So they try to like also manipulate the environment after the initial time and try to get vision of the blue color hiders. Yeah, so you can see like over time as the model iterates and learns, like you can see like the agents actually start to find very interesting strategies. So over here you can see the hiders remove the ramp away from the seekers so they cannot use the ramp to climb the wall. So eventually like I can see like they reach a very high level of play, like even higher than what humans can do. Like for example, they exploit certain bugs in the game in the physics engine to do this. So here you can see the seeker, he locks himself in and like he locks the RAM as well so that the hider cannot use it. But then the hider exploits the physics engine. He drags the box around, do some mad hacks, and then he got on top of the box and use even more mad hacks to surf around and then eventually climb in. Yeah, so that was pretty cool. Yeah, so it's pretty cool what reinforcement learning can do. Yeah. So moving on, maybe we'll just like give you all some intuition behind how neural networks work. Like actually, neural networks sometimes it may sound quite daunting, but the intuition is actually quite easy to grasp. So we'll start with a linear neural network first. So like neural networks normally are composed of multiple layers. So you can think of each layer as a collection of neurons performing the same operation. Okay, so like we'll talk about the input layer first. So all the way on the left, like underneath the word features, like you can see the input layer. Yeah, so in the input layer, the model looks at certain features. So features are the details that the model observes. So over here, we have the example of an X1 feature and an X2 feature. So on the right hand side, you can see like many different dots. Those are the ground truths. Okay. Yeah. So like for example, like for the X1 feature, like you can see like it denotes like the horizontal coordinates. So like for example, there are some dots that are in blue. You can see like those are +1, and then like some are orange. You can see it's -1. And then like X2 denotes the vertical coordinates. So like from this ground truth you see over here at the output side, it actually denotes the exclusive NOR, the exclusive NOR gate. Yeah. So like when both X1 and X2 are positive, or if both X1 and X2 are negative, like the value is positive. Otherwise it's negative. Yeah, you get the idea. Yeah. So here when we run a fit, we can see that the linear model does not fit the exclusive NOR function very well, which is quite intuitive. Yeah, because it is obviously a non-linear function. Right. Okay. So now we will add some hidden layers, and then we'll see how the model fits. Yeah, and then like as you can see, okay, like the training will take a while, but then you see the effect is quite obvious. Yeah. So what hidden layers are is basically they help to learn intermediate representations. Oh, like you can see like the model fit like quite well this time around. Like so, what hidden layers help to do is to make the model more be able to understand more complex things. So this is what we call as improve the complexity of the model. Yeah. So oh sorry, like go back to the slide just now. I mean the demo just now. Okay, so like maybe an observation you can make with the output over here. Like I can see like like the split is not really perfect. I can see the vertical and horizontal split is not exactly at 0. So like this can be largely due to two reasons. Like one of it is the model is normally initialized randomly. Yeah. So and normally the initialization doesn't start at 0 but slightly away from 0, and that actually matters. Yeah. So as it fits towards the data, you won't get a perfect split over here. And then like the second reason is how the data is being distributed. So maybe sometimes the points are not that close to 0, and then you will have a more less perfect split. Yeah. Okay, so maybe we move on to the idea of how these hidden layers add some more complexity. So like actually without activation functions, these hidden layers are actually quite useless. If you just stack the hidden layers like this, like no matter how much you stack, the entire model will still be linear. It'll be equivalent to just like having like a single layer. Yeah. So These activation functions are actually quite important and they're not usually placed after each layer. Yeah, so most traditionally, we have the sigmoid function, which is quite similar to how or how people think the brain works. It's either a 0 or 1. Yeah. And then however, there's some drawbacks of this sigmoid activation function, because the mean is at 0.5, which is not ideal. After that, people move on to use the hyperbolic tangent, which has a similar behavior, but the mean is at 0. Okay, however, this also has its own drawbacks. You can see that it requires the exponential function, which is quite computationally intensive. So what we use nowadays, like what most people use nowadays, is the value function, the rectified linear unit, which is just when x is more than 0, it's just a linear unit. When x is less than 0, it's just nothing. Yeah, and then there are also different types of the value, like the leaky value or the exponential value. Because the value has its own drawbacks as well, which is the dead neuron issue. Like a lot of these uh, gradients. Okay, like later we'll go on to how the network learns, but a lot of this learning is just lost because on the left side you can see that the gradients are just destroyed. Yeah, so we have the leaky value or the exponential value to deal with that. Yeah. So maybe now we move on to some intuition of how neural networks learn, right? So okay, so on the left over here you can see exploration space. Like actually the height of each point over here, you can see is actually like an error or a loss that is being computed. Yeah, so what the neural network tries to do is to try to approximate a function. So what it does is reduce this error as much as possible. So you can think of it as a minimization problem. So when you go higher in math, you learn about optimizations. Yeah, this is actually how it works. So basically it just goes down the gradient and find the lowest point possible in this space. So on the right hand side, you will see backpropagation. Okay, so the idea is like the loss is first computed at the end, like all the way on the right side. That's the last layer. The loss is first computed there. And the loss denotes the difference between what you want the model to predict and what the model actually predicts. And then it computes the gradient with respect to parameters. Okay, we shall look at the last layer, the last hidden layer first. So we compute the gradient with respect to the parameters there, and then we take a step towards the direction to reduce the loss. And then this is performed iteratively forward. So from tail all the way to the head of the model. Yeah. So what this does is basically it does improves the model by reducing its loss lah. Yeah. Like intuitively you can just see on the left, it's just a minimization thing. Yeah. Okay. Yeah.
All right, so moving on, we'll actually explain one common neural network, which is the convolutional neural network. The convolutional neural network is actually really common in computer vision problems especially. And to explain it, we actually have this in-browser tool again, which is the CNN Explainer. Yeah, feel free to copy the link if you want to see in your own. You can play with it during your own time or yeah. Okay, so in this example, we actually have the input image of a cup of espresso, as you can see here. And we then have the output, which is 10 different classes. So the model will select out these 10 different classes, which class it thinks the input image is. And in this case, we can see that it correctly selects espresso. So for the input, first it is split into the red, green, and blue channels because I'm sure as you understand, images can be represented as RGB. So the thing is, first, the RGB channels will be fed into a convolutional layer. So the convolutional layer actually will have different filters. So right here, for example, right now this is the filter for the red channel. So the way it works is that the convolutional filter is actually, in this example, is a 3x3. We can tell us 3x3, for example, because there are 9 parameters, each 3x3 in size. So the thing is actually you'll take a small slice, a small 3x3 pixel slice of your image. And then it will start to process them by multiplying the values of each pixel. In this case, the intensity of each pixel normalized to between 0 and 1, and then multiplied by the different weights in the filter. So for each pixel, we have a weight. So for example, for the first pixel, the top left pixel, we have a weight of negative 0.3. And for this pixel, we can see that the pixel has a value of 0.15. So we do this and we sum up the values. It's basically a weighted sum. It's similar to a weighted sum. And then we get output, in this case, negative 0.08. So that will help us calculate the output image. So by this, we are able to calculate the value of the output image, and then it does this across the whole red channel input. And then we do something similar for green, but with different weights. So as you notice, the weights actually have changed. The weights actually slightly different from the red one. And that's why we get a different, and also because the green's input is different from the red's one. So we do this for the red, green, and blue channels. And then we sum everything together and add a bias value. We can see over here that the bias is 0.1898. And then for each of the values in the output, we'll sum the red, green, and blue outputs. The red, green, and blue convolutional outputs, and then we add the bias unit, and then we get output of the convolutional layer, which we then feed into the value layer. So just as I mentioned earlier, the value layer actually would do a max of 0 and the input. So in this case, for example, we see that there's a lot of red values which denote negative values. So the output for the value units for those would be 0, because the max of a negative value in 0 is always 0. But we notice that there's a little bit of blue, which are positive values along the rim of the map. So these values are passed through to the output. So for this, for this model, it will have one convolutional layer followed by a value activation layer. And then from the value activation layer, it will feed into another convolutional layer. Then here we can observe that we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 different convolutional filters for each layer. And then there's also this max pooling layer. So the max pooling layer it's a little similar to the convolutional filter in the sense that it takes a small slice of the image, but instead of doing like a weighted sum of the pixel values based on the filter's weights, it actually takes the max. So for example, in this example, the max pooling filter size is 2. It's a 2 by 2. So out of the 2 by 2, out of the slice that it took, the 2 by 2 slice that it retrieves, it actually searches for the max. So for example, in this slice, the max is 0.11. So that's the output that's the value that's passed into the output as well. So through the convolutional value and max pooling layers, the image actually slowly detects the salient features. So for example, you notice that here it's observing the cup. So right now here we can detect the cup, and you can see the features that the model is detecting, which help it to eventually come to the conclusion that it's an espresso. And yeah, I mean, it's really interesting. You can try out this link on your own. You can see all the different connections and how the outputs are calculated and how the outputs are used again as inputs into the next layer. And also, it also has a really in-depth explanation on the different parts of what I just mentioned. Right, moving on. So another very interesting tool that you can play around with is the Teachable Machine by Google. So for example, over here, we actually prepared some data. So for example, we actually had 136 image samples of having a human. So for example, video, right now we actually can see that if we take more images of me sitting here, which is a human present, and we have like 117 image samples of no human being present, and we can train a model just like that. So we're training a model to detect between the two separate classes, one being human present and the other having no human present. So we have relatively small images, so the training can take place relatively quickly. And right now, if we feed in the input, it's able to detect, for example, that I'm sitting here and there's a human present, and the model is able to accurately detect it. If I move out of the frame, we can observe that the model is able to accurately detect there's no human present in the frame as well. However, if we actually introduce something else, for example, let's say I pick a watch, and then I remove stay out of the frame, and I show this, I show a watch. The model is not able to accurately detect it very well because the model was not trained on such data, which is also a really common problem in machine learning. So it's really the idea of being a greater diversity of data, which is really important in order for our models to work better.
Yeah, pretty cool. Right, so just ending it off. Okay, so what we see just now is that machine learning actually has many different applications. So anything that has data or anything that's optimizable, yes, you can apply machine learning to do it to a very high competency. Yeah. And also like we what you showed us now is also machine learning. The concepts of machine learning is actually not that difficult to grasp, and we believe that you can learn machine learning too. And also we are very excited, and the world is very excited to see what you can create with machine learning.
So, following from this talk, if you're interested in learning more about machine learning, some resources you might want to refer to, I would highly recommend Andrew Ng's machine learning course on Coursera. It is a really good introduction to the fundamental ideas of machine learning, as well as a really quick introduction. And it's just generally interesting. He's a pretty great teacher. You also can learn from the tutorials provided by the different machine learning frameworks. So for example, the two big machine learning frameworks these days is TensorFlow, which is TensorFlow and Python, and PyTorch. Both of them are in Python. So if you want to do machine learning, I highly recommend Python. But you can see the different tutorials here, and yeah, you can learn them. You can pick up the basics of machine learning relatively quickly, especially because the frameworks help to extract a lot of the complicated math away. So you can build machine learning applications easily on your own too. And yeah, if you want, you can always hit us up. My email and Rhea's email on the screen. And yeah, like Rhea mentioned, we're really interested to see what you will create in the future. Thank you.
Yeah, thanks.
All right, thank you, Ming and Rui for the wonderful presentation. So hopefully, if you were not convinced by yesterday's machine learning workshop, you'll be convinced to consider using machine learning in your submissions. For now, as I can see, there is the Q&A link in the chat. So please take some time to fill in the Q&A for the speakers if you have any questions. And we'll be sending the questions over to the speakers since they're not here today, and we will try to collate the answers and send it back to you. So I shall give you now 3 minutes to submit some questions to the speakers.
If you guys already asked your questions or you guys don't have any questions, you guys can go on a break and be back by 8:45.
So far, there's only been one question. So if you guys want to ask some questions, please take the time now to do so. as Mr. Gee has just sent in the chat, the slides are in the chat for those of you who want the slides. So I see there's some questions in the chat about how to name yourself on Zoom. You currently cannot change your name in the Zoom room due to security reasons, but if you want to be admitted, you have to have the correct naming convention. So you have to change your name outside of Zoom by either using the Zoom app, or if you have an account, you can sign in to the website, the Zoom website, and change your name from there. Okay, the time now is 8:45, which means we'll be moving on to the next workshop, which is Introduction to Machine Learning Part 2 by Ik Ting and Min Jia. They'll be continuing on what they have left off yesterday by programming a few programs related to machine learning and what they have been teaching us using a teachable machine yesterday. So without further ado, we shall let them take it away from here.
Hello everyone, and welcome back to the Introduction to Machine Learning workshop. Again, I'm Yik Ting, and I'm here today with Min Jia, and today we'll be covering the second session of our workshop. So yesterday we covered about teachable machine, and we let you play around with some of the values. So today we are going to implement some of the models. Instead of using it only in teachable machine, we'll be using it outside, which means that we'll be implementing it today, specifically in Python and JavaScript. So here's a run through about what we'll be doing today. Sorry, please give me a second. So today we'll be implementing a mouse mover. So I'll be going through that, which is how you will implement a Keras model into Python. While Min Jia will be going through the don't touch phase, which is implementing a TensorFlow model into a website, which is the JavaScript version. So without further ado, let's start. So I'll be starting off with the mouse mover. So can I invite all of you to join us over here at my GitHub link and view my code at go.buildingblocks.sg/intro to ML/mouse. So before I would begin, I would probably like to go through a demo of, or at least explain to you what the end product we are expecting to get today. So a mouse mover basically is whatever it suggests, which means that I can move my mouse, but instead of moving my mouse with a mouse, I want to move my mouse cursor with my head, which means that I can tilt my head up, down, left, or right to move my mouse cursor on the go. So for example, if I tilt up, I want to expect my mouse cursor to move upwards. If I tilt down, I want to expect my mouse cursor to move downwards. And this is something that can be done with machine learning, with simple teachable machine, and I will demo it to you now. So what I'll do is now that I will head to teachable machine, and for this for this Python implementation, you guys can choose whether to follow me or not. But afterwards, I will be using a module which is PyAutoGree, which many of you might not have. So it is not compulsory to follow me along through this example. You guys can just watch and learn the concept of implementing it into Python. However, Minjia later will be going through implementing it into a website, so you guys can follow through that. And I hope you guys have signed up for your GitHub account as well, because you'll be using that later. So we'll now be starting on the teachable machine. So I will turn off my camera and Zoom to enable my camera on teachable machine. So what I want to do essentially is that I want to create 5 classes of photos. So my cam is on here, and I want 5 classes of photos. What do I want? I want the mouse to move up, down, left, or right? So which one is the 5th one? So the 5th one is actually neutral, which means that I'm looking straight into the camera and I'm not doing anything else. So other than that, I will need up, down, left, and right. So first one, I'll name it as neutral, which is just me staring into camera for 10 seconds so that you can look at my face, but at the same time, I will try to get a bit of movement as well, so as to not to overfit the model. I mean, this model essentially is still overfitted because I am using the same background, but for demo purposes, for this short time of period, I'll just be doing this. So the first one is me staring directly into the camera. Second one, I want pictures of me looking up. So I will put up and I will look upwards, and you can see my glams. And so essentially you get what I'm doing. I'm taking pictures of me looking at all different directions. So because of this short timeline of this workshop, I can't afford to spend all my time taking photos and showing you my beautiful face. So instead, previously, I've actually taken all the photos and trained the model, because training the model with so many image samples takes quite a bit of time. So if you look at this, this is my neutral, sorry, let me turn off my cam over here. This is my neutral images over here. So all these are me looking straight, this is me looking up, this is me looking down, left, and right accordingly. So I have 5 sets of images over here, and I've trained my model. So right now I want to test out my model, and I'll turn on my webcam over here. So in teachable machine, it is loading now. You can see that I'm looking straight into camera, it's neutral. I'm looking up, it's showing up. Okay, if I'm looking down, it's showing down. Although the accuracy may not be especially high because there are 5 categories and all of them have my face. So it's kind of essentially similar, but accuracy is kind of there. You can see that the classes change quite a bit. So what I've done is that I have exported my model. And exporting my model, to answer your question yesterday, because I haven't found out, because from all my testings, I have just managed to, I can see the TensorFlow tab. So maybe you could open a consultation ticket and then try and screenshot your website, and maybe I can try and help you out better. Because on all the attempts that I've tried, I've managed and debugged, I've managed to open up this TensorFlow tab. So probably it's a problem on your side. I'm very sorry for that. You can open up a consultation ticket on Discord. So heading back to this project, now I want to export my file as a Keras file. I want to use it in Python, right? So it's a Keras file. Remember the naming is Keras. So I tap on TensorFlow, which is the second tab. All of you following me so far, if you have any questions, feel free to slow me down. Yeah, so this is a TensorFlow, and I will click on Keras and I'll click on download my model. And it will take a bit of time as well, but it will load and it will send me a zip file. I'll download a zip file. Give me a second. Class 5, very sorry, class 5 is right. I forgot to rename, yeah. Very sorry for that. So it's up, neutral, up, down, left, and right. Okay, so I've downloaded my model and I'll wait for it to load. It's converting the model. So now I'm going to show you my folder. My folder is essentially, these are my preloaded models that I downloaded this morning, right? So for example, I want to redo this. I have this zip file. I open up this zip file. I extract the files inside. So you can see that inside this Keras zip folder, there are 2 files. Sorry, let me turn on my camera again. Yeah. Okay, so you can see that there are 2 zip files. There are 2 files inside my zip file. So one of them is the labels file, and the other one is the Keras model .h5. So the labels file, if you open it up, you can actually see it's just 5 things, which name neutral, up, down, left, and class 5, because I named it class 5, but essentially it's right. So what this labels file is actually telling you is giving you the information on how this model functions. So this model actually creates an output of 5 numbers. However, this Keras changes it into 0. So Keras gives you an output of 0, 1, 2, 3, 4, or 5. But with these labels, we are able to print out the class name instead of just the numbers. So let's say Keras predicts 0, it can tell me that it is neutral. So this labels is essentially for that. Sorry if you can't see it, it's here. Okay, so now I'm heading into the Keras model. So this is a H5 file, and H5 is for Keras. So what I will do is that I will drag these 2 files into my folder. And in my folder, which I have here, I have a Python file, and I have the 2 files that I dragged in earlier on. So it's a Python file, and I include the 2 files from earlier on. Now I head into my idle. So I have opened my Python idle, and this is a lot of code, but I'll try to walk you through it. So try and follow me along, and if you have any questions, feel free to ask. So code is also in GitHub. So starting off with the modules, you can see that at the front, I import all the necessary modules. If you have followed the Python workshop, you've known that modules are some packages that you can import, which have some extra functions that you can use in Python. So in machine learning, a lot of times you use NumPy, we use CV2, and these are some computer vision models that you need to use. From time import sleep, this is to slow down my program, so to reduce its processing power, so later it doesn't lag so much. And you import this TensorFlow.Keras model. This allows me to work on the Keras model and need to process it. So I also need to import TensorFlow. And so these are all the modules required for my computer vision. The very last one is PyAutoGree. So can admin send the chat to PyAutoGree now? PyAutoGree is essentially just a module to automate a lot of processes in my computer. So if you look at the PyAutoGree documentation that admins have sent out, which I will also show here now on the screen, if you check it out, you can see that actually there's a lot of functions. So what I can do is that I can actually write stuff on my keyboard. I can move my mouse cursor. I can press buttons on my computer. I can press it many times. So it's kind of like an automation system for my computer. The reason why I didn't want all of you to follow along, because this requires the download of the PyAutoGree file through the pip function, which can result in a lot of problems. However, if you guys would like to try, go ahead, and I'll be free to answer any of your questions in the consultation area in the Discord chat. So what I did was that I imported PyAutoGree, and now I'll be able to use the functions for PyAutoGree from now on. So starting from here, there are a lot of comments, so just follow along. Firstly, I will want to set my laptop's webcam, right? So my laptop's webcam, I open up my webcam, which I'll do later when I run the code. Before that, actually, let me just rename my labels because it was class 5, it should be right. Very sorry about that error. So now I have neutral, up, down, left, and right. Okay, so these are my 5 labels. Now I also need to include a list of labels here. This is to allow Python to reference my labels. So in this case, it's the same order: neutral, up, down, left, and right. So these are the 5 possibilities of photos that I have, which at the same time are in the teachable machine. So now what I will do is that I will load the model. So if you look at this, I'm linking it. I am asking TensorFlow and the TensorFlow module to load my model. And in this case, I'm loading this model named karasmodel.h5. This is the default name that is downloaded by Teachable Machine. So I'm loading this H5 model right here. Let me check the chat. Yeah, if you have any questions, go ahead. Feel free to open a ticket in the conference consultation. Okay, so what I'm doing here is that I'm loading the model. After I load the model, what I want to do is that I want to keep repeating. So this is a while true loop. While true loops basically is a while loop, but it keeps on repeating. So what happens from here is that, again, let me check the chat. Yeah, H5 allows you to store a lot of numerical data. So in this case, it's a lot of data from the teachable machine. And NumPy is actually a set of arrays that we process in machine learning to allow us to be able to predict images. So in this case, there's a lot of data, a lot of numbers actually inside this H5 file. So when I load it, I'm allowing myself to view all that data and process it. So what I'm doing here is that I am reading if my camera is on, I am able to on my camera. Then I will flip my image. This is because the camera automatically flips itself when it's on. So in this case, I want to flip it to make sure it fits the same angle as my teachable machine. So afterwards, I want to resize the images. Why do I want to resize the images? This is because there might be a lot of different details which the machine might process differently if I have different sizes. So when I resize the image, it allows me to make the image much more standardized, and it makes the data less biased. So in this case, I'm resizing the images and then I'm converting it to NumPy array. So now I'm taking, okay, so what happens over here is that I'm taking a frame of my camera, and from that frame, I'm converting that frame, which is an image, into a NumPy array. And when I convert it to that array, I'm able to compare it with the Keras H5 file in that case. Yeah, so afterwards, what I do is that I want to normalize the photos, and then normalizing the photos means that I want to standardize them and standardize the values. Afterwards, I want to predict the class. So I just do model.predict, and I put inside that as my argument, the image. So if you don't understand all this code, it's okay, because I didn't write all this out as well. It was taken from here and there. So a lot of times you have to consult various sources when doing computer learning, and using this Keras module is one of them. So afterwards, I use PyAutoGui. So here I'm introducing PyAutoGui, right? So I'm using this module PyAutoGui. And what I want to do now is I want to get the position of my mouse. So I want to get the current position, and out of this current position, there are 2 values. One, which is the X value, which I save it to this variable named current X, a Y value, which I save it to this variable named current Y. Following me now? Any questions? If you need me to slow down, go ahead. So afterwards, what I do is that because I have predicted my model and I have used my labels in this case, then I have printed out my predicted class. So whatever I've predicted, it will now print out in my idle. So there are 5 predicted classes, right? So in this case, if my predicted class name is neutral, because I'm now implementing in Python, so all I need is this list. Actually, I don't need this labels file, because I have chosen to use it in Python. However, if you want to use it in other contexts, you might need this label file. In this case, I am just using this list of labels, and I know that 0 is neutral, 1 is up, 2 is down, or so on and so forth. So for example, if in this case, now it's a bunch of series of if statements. So if the predicted class name is neutral, because I'm looking straight into the camera, I do not want the mouse cursor to move. So I will just pause for 1 second. So this is when I introduce the sleep module. I pause for 1 second, and then afterwards I continue. So I do not do anything after that. Now comes the other part, which is the prediction if my class is left, right, up, or down, or up. And later, I'll be implementing the pyautography functions that allow my mouse to move. However, currently, I just want to print out my predicted class name and see whether my model is working fine. So I'll be implementing all these if statements later. And finally, if all is fine, if I want to close my windows, I can press Q and it will end the program. But usually I just do a keyboard interrupt. And afterwards, I'll just destroy all the windows so that it doesn't build up in my computer. So I've run through all the code. Is everyone okay at this point of time? Before that, I'll now turn off my video over here so that I can, pass is fine, yeah. Now let me just turn on run my Python file. So this takes a lot of time to load on first run. However, I preloaded this file in the morning, so it should run better now. So it should take a while to load because of all the modules, and I'll wait for a while. Meanwhile, again, if you have any questions, feel free to ask in the chat. Okay, so I received a warning, but yeah, it's okay. So you can see that the files are printing up now. So now I'm looking straight, it's neutral. Actually, I should here. It's slightly off because I didn't train it with that many data sets. If you look at it straight, it's neutral. If I look at it up, it's printing up. I'm looking at it down, it's going down. Okay, so now I'm just essentially printing out my predictions that from my model in class in a teachable machine. Okay, now if I'm looking left, again, it should work. It says left. If I'm looking right, so these are to check whether my data set is working. So it works. So all up, down, left, right, neutral, all works. Okay, which means that my predictions are going well. It's quite accurate. So now what I want to do is I want to implement my pyautography functions. Very sorry for the indentation because it's very messy. Yeah. Okay, so what I'll do now is that I will uncomment these codes. So, and I'll explain all along the way. What I want to do here is that I want to use the pyautography module, and I want to move my mouse cursor. So if you look at the documentation, move to represents my mouse cursor. Just a second, let me end my idle so that I can turn on my camera. Okay, now I am using, now I'm gonna, yeah, there's a lot of indentation problems here. Okay. Now I'm gonna use move to. So as a move to function, it takes in two arguments. One which is the left, one which is the x-axis of the mouse cursor, and one is the y value of the mouse cursor. And the last thing is optional, which is duration. So what I want to do when I want to move it to the left, in a generic like computer screen, x-axis refers to the horizontal axis and the y-axis refers to the vertical axis. And so when I want to move it to the left, I essentially want to decrease the x value because I am moving my mouse cursor to the reduction value of the x-axis. So that's why I want to reduce it by 80. And I want to keep the y the same because I'm not moving it up or down. So in this case, I'm just changing my x value. If I want to move it to the right, I want to increase my x direction value. So I'm changing my x value to the current value of my mouse cursor plus 80. So I'm moving it to the right. Okay, and I'm keeping a y the same because I'm not moving it up or down. But now for down and up, you can see that I am actually, I'm not changing my x position because I'm not moving it left or right. Instead, I want to move it down. So because what happens is that the y value increases downwards. So I want to keep increasing the y value when my prediction is down. And as for up, I want to decrease my Y value, so it moves up. So in this case, this code should be able to move my mouse cursor. Now that I've saved the code, and let me run it again. Indentation errors, sorry, give me a second. There's a lot of indentation errors you might face when implementing in Python. So just have to fix it at times. Okay, sorry, very sorry for the error. Let me try and I think initially was that. So let me remove all the, there's a lot of indentation problems in this code. Very sorry. Okay, so again, I have cleared out all my comments. So this allows me to run the PyAutoGui move-to functions. So now I need to turn off my cam over in Zoom. So it will take, again, some time to run. So later I'm going to talk about how I can implement, I can use more than PyAutoGui because Python is so versatile. So I can use a different, so many series of functions that I can implement in my code. So outside of teachable machine, I can also use the model and I am still able to run my code. So if you look at, I'm not moving my mouse cursor, I'm leaving my mouse cursor untouched. I am looking straight into camera, so it's neutral. Let's, so my mouse cursor is currently over here, okay? So now let me move down. You can see that my mouse cursor is moving down. If I'm moving left, you can see that my mouse cursor is moving left and it's over here now. So it's slowly moving left and I'm not touching the mouse at all. So now I'm gonna move right. And you can see that's moving right. Yep. And last thing is up. So my model is still pretty inaccurate, but it kind of does the job. And although this might not be the best way to move your mouse, but it is kind of a fun way to explore and implement this function. So what I just did was that I used teachable machine, a combination of teachable machine and Python to move my mouse. Okay, so PyAutoGui has many functions. So I now want to spend more time exploring other functions. Let's say I want, if I look at the documentation and I go to keyboard control functions, okay, I can type, but that works, but I want to do something better, maybe something that we can all actually use in our daily life. And so you can see under these keyboard keys, there's a list of all the functions I can actually use. Let me make it bigger because it's really small. So what I do is I just pressed PyAutoGui.keyDown and I insert one of these as my arguments in order to press the button. So now I want to use, because now what I want to do is I actually want to play music and pause music using my face as a control. So instead of moving my mouse cursor, I want to use play pause. If you can see, play pause as my argument in order to play or pause my my music. So just, sorry, the stream ended, give me a second. Okay, so what I want to do now, I want to do PyAutoGui.press play pause. And let me share my screen again because it went down. Okay, so over here, let's say I now do not want to move my mouse cursor anymore. And instead, I only want to move, I only want to do something when my mouse, when I'm looking up. Let's say I want to play or pause the music when I'm looking up. So in this case, I will type PyAutoGui.press And in this case, I will write play pause. Sorry, I think it's play pause, right? Should be play pause. Play pause. So play pause. Okay, so what this essentially does is that when I'm looking up, and let me move this to a new statement. My indentation is all over the place. Sorry, give me a second. Let me just use this line of code instead. Okay, so play pause. Now I'm gonna press play pause, but because I'm not playing any music currently, so let me go and play some music on YouTube. So just gonna casually look for a song and play it. So now what I want to do is I want to turn off my cam again over here in Zoom. I'm gonna run my Python, and while my YouTube is loading, let me ignore the advertisement. And while my Python is loading, let me shut it down. Can you all hear it? So now the music's playing. Now the music's playing and my Python's loading, right? So now only when I look up, it will pause or play the music. So again, let me wait. And you guys can enjoy the music in the meantime. Again, it takes some time to load. We're gonna load now. Okay, so now I'm looking down. So it's just predicting down. So it's not supposed to do anything, right? It's predicting down. I'm looking down, so it's not supposed to predict anything. Yeah. Okay, now I'm gonna look up. So it pauses the music. And because I've looked up too long, so it pauses the music, pauses and plays the music again. So let me look up again. Look, I've paused the music with my head control. Okay, so this is essentially one of the things you can do in Python. And again, I can implement so many functions because Python is so versatile. Let me look up again just to test the music. It works, okay? So with that, I have come to the end of my demo. And these are some of the functions you can do in Python. My head control is still going on. I think I'm just gonna leave this on one day and actually just play pause music using this method. It's a very cool method of doing it, I feel. And yeah, again, you can do it in a lot of your prototypes that you'll be creating today and tomorrow for the AI Web Edition. So I'll be looking forward to see what you can implement with Python. So hopefully my demo helps. The code is in the chat just now. So now, I'm gonna pass on the time to Minjia, who will be going through the JavaScript side of the implementation.
Okay, so hi everyone. Today I'll be going through the second part of the course where you will be making your own teachable machine model and you can integrate it into a HTML website. So for this, do not touch your face model. Do follow along and I'll be going slower. If I'm going too slow or too fast, please note down in the chat group. Yeah, so first off, this website is a model where you can classify us touching and not touching our face. So this is in line with our COVID-19 situation, and this will be hence a useful application for our use now lah. So let's explore this website because this will be roughly how it will work. So it will activating face touching AI, and I'll be sending it into the chat group. So all of you can follow along as well. Okay, so first, they tell you to take a video not touching your face. So you just keep your hands down. And you take and...
So essentially what this is trying to do is that because COVID-19 may help you reduce the chances if you don't touch your face, it will reduce the spread, hopefully. So this website encourages you not to touch your face.
Oh yeah, for the don't touch your face part just now, you can move your hands elsewhere, just don't touch your face with your hands. Now you can take a video with you touching your face. Like also move your hands around so the model will be accurate. So now they'll be able to predict whether you're touching your face or not. So as you can see when I do this, the model didn't tell me not to touch my face. But once I touch my face,
No,
they'll say no, reminding me not to touch my face.
no, no.
Okay, so like the model will be very, very similar to this. It's just that it will not scare you by saying no all the time. So now, how can we go about doing it? We will go back to Google's Teachable Machine like I've mentioned yesterday. It's the same way. So we still go towards the image model, image project. And we will have two classes, unlike things, which is 5 classes. But for the 2 classes, we'll name it touch and don't touch. Also take note of the capitalization and the spaces and as well as the hyphens and everything, because actually when we implement it into the code, my code is based on these names of the classes. So it'll be easier if you all can follow along. Are you all up to this step right now? Okay. Now we put on our webcam. Same thing, we hold to record, we toggle it off, we save, then we record 10 seconds of us touching our face. In all directions, like just now, when we play with the Don't Touch Your Face website, we can move our hands around, touch with one hand. Then now for the don't touch, we will keep our hands off our face, or we can also move our hands otherwhere else, like this, as long as you're not touching your face. So now we train our model. Again, this may take some time, so I'll wait a little here. If you all have any questions, please put in the chat and me and Ik Ting will try our best to answer. When they tell you to wait because the page is unresponsive, you just click OK, then you also don't switch the tab away.
So just now Minjia took the 2 videos in the website. I think essentially it will just, it's kind of the same thing as taking images of these 2 classes, because firstly she took a video of her not touching her face, right? So likely the website is taking screen grabs on the video and training the model. But in that case, it's just comparing, it probably has a bit of a pre-trained model there. But in this case, you're purely creating 2 classes, and so that's why we are trying to classify whether we are touching our face or not.
And Mr. Gee's question, whether putting your hand in front of your face but not touching it is still considered touching your face by the model, because we only took it like 2D. But if we were to do 3D, if we were to train our model in 3D, then maybe it will be easier to detect next time. But I think we can keep it simple for now. So as you can see, when I don't touch my face at all, is 100% sure, the model is 100% sure that I'm not touching my face. But once I touch my face, it is 100% sure that I'm touching my face too. So this shows that our model is pretty accurate, and I'll be waiting a bit here for some of y'all in case y'all have errors. We can wait for about 5 minutes. Meanwhile, if anyone has any questions, please type it in the chat. Meanwhile, for the rest of y'all who are done, you can also open up a tab in your computer, go to github.com and sign in. Like if your hands are there, but like you're not touching your face, it will be classified as don't touch.
I think in this case, it's looking at whether you cover your face with your hands or not. The machine may be more trained on recognizing whether the face is covered or not. So in this case, if your hands are there, it should still be fine. In Minjia's model, at least. Again, it depends on how you train your data as well.
Yep, so you'll take note when you go for the, when you take your don't touch, you can also move your hands around instead of just not using your hands at all. You can move it like this. So it can classify as not touching too. I think we can wait about 1 more minute. There is not much technical errors going on. All right, I think we can continue. Now, since our model works in the preview, we can first click on export our model. Take note, you are going into the TensorFlow.js tab. You click download here, this button, and click download my model. So I'll be going off screen share for a while to unzip my file. All right, now since I've unzipped my file, let's head to github.com. And we shall create a new repository. So the repository name, you can name anything you want. I will just name my JavaScript, don't touch your face. You can add a description if you want to. Remember to put it to public, a public repository, and create repository. So now you click on getting started by creating a new file. So for this file, it will be HTML. So you can name it anything you want as long as you put a .html at the end. I'll name my index.html. So actually I had some errors previously when I was running the code. So you need to commit the file first, otherwise the GitHub pages may not load. Then you go to settings. You should check the GitHub pages first. So and click check it out here. You change your branch to main and you save. If any of you are not keeping up with at this point of time, please note it down in the chat. And we'll wait for our site to be published.
Regarding Sogat's question, yeah, unfortunately, it will take some time on some computers, and although closing some other programs might help, but a lot of times it will still take a lot of time. Yeah, it's fine if you're unable to follow. Just watch the live stream, and it's a way of implementation or that you can use in JavaScript. So just take from this workshop. Now, main aim is not for you to exactly follow the demo. As long as you get how you can implement it in JavaScript or Python, we're happy with that.
Okay,
For Sogat, if you're still facing any questions after this, you can head to conference consultation and we can help you out, because we understand it's taking some time, but due to this workshop timing, we can't wait for too long. So we'll have to carry on with the workshop. Thank you for your understanding.
Okay, so now my GitHub pages is working as it can show in the new page. If any of you have 404 error, please note down in the chat right now. I'll be waiting for a while in case some of you may have site not found errors. Maybe about like 1 to 2 minutes. Okay, I see no errors as of now, so I'm assuming everyone is done. So now I'll be explaining more about the code. And yes, we'll be sending you the link to the repository for you to copy down the codes into GitHub. So now for this segment, it is basically basic HTML to set up the web page, which also includes the link to your teachable machine, to the model in your teachable machine. And for this part, take note of this constant URL equals to this naming, because for the naming of the model, do take note of your capitalization, hyphens, and spaces, if any. Because for this, if you're following my code, remember to either change this part to your model's name, or you can change your model to tm my image model. First, for this part, we are defining our constant variables. Then we'll be using an async function to load up the image model, as well as setting up our webcam. And we will also load in others such as metadata and other data which will enable our model to work. So this next chunk of code is referring to our advanced webcam setup. We will need to we can flip our webcam, so we put it as true. Then we also have to ask the user's access to the webcam. And we are defining the webcam size too, and the height and the width. So it's 200 and 200 in this case. Now we will append our elements into the DOM, which is also known as the Document Objects Model. This will ensure our structure and the content of our web page. So our code is showing us that we append the elements. It is also creating new elements at the same time. We will then update our webcam frames in the background, so it will not hang there as only one image of ourselves. We then run the webcam image through our image model in the next async function to allow the model to predict if we are touching our face or not. The predictions will be able to take in video HTML elements as well as images. So the for loop generates the prediction percentage for our webcam video input. After which our predictions will be expressed in words. That means that if our prediction for touching our face is more than 0.3 or 30% here, then our web page will remind us not to touch our face. Otherwise, it will pass off saying that we are safe. So this is the completed codes, but I'll be sending you the link to my other GitHub repository for you to read the code. I'll be waiting here for everyone till they are ready. Or you can access this link here. We'll be waiting about 1 minute for you all to access and look through the code inside my repository.
If there's any part of the code you don't understand, feel free to voice out and we'll address your concerns.
Regarding implementation of Python in HTML, for this code, I don't think there's a way to do so, but I think there will be some modules available online, but you may have to download them. I'm not very sure about it. Maybe Ikting, would you want to also explain?
I'm actually not that sure as well, but I think there should be some way in implementing Python code. You probably have to work with some other module. But I think as Bowen mentioned, Flask might be a good option as well if you are considering Python and if you're familiar with Flask. Regarding Zili's question, so if you look at the code, Minjia can go up to the if you look, so I'm looking for this division. This because in HTML we have many objects. So in this case, this object is named webcam-container. When I'm appending the child, it means that I'm adding inside this sort of container, I'm adding another HTML item, which in this case, this is a canvas. So I just want to add it into a division, which means that I'm adding it into that particular part of the page. Yeah, hopefully that answers your question.
Okay, so I think most of you are done. So I'll be going on. So for this part of the code, I'll be copying and pasting it into my index.html. So we'll go back to code. Then we click on index.html. Then we edit the file. For the rest of you, you can paste the code, copy and paste the code from my repository. So now we commit our changes. So we have our code done, but we'll still need to add our model into the GitHub project. So we click on Add File, then Upload Files. So I will be having my screen share off for a moment when I drag in my image model. We wait for it to upload.
So if you look in the folder, there's actually a model.json file. There's a weights.bin file, which is the same as the weights file that I had earlier on. And the last file is metadata.json. So the metadata gives some information about the model itself. So all these three files are required to load the model in JavaScript. So mainly the model.json file acts as the Keras file in Python. It includes all the numbers and is able to load the data which is inside the model.
Okay, so is everyone following up till this stage? If not, you can type in the chat or something if you want me to slow down. So I commit my changes. We're almost done at this point in time. I think we can wait for about 1 minute in case you all need some time to catch up. Okay, now we'll be moving back to our settings and we'll click on GitHub Pages. So scroll down, click here. Then we can view our site. So as you can see now, they will have a teachable machine image model. You can press start. And this, after pressing start, the camera will load up. If your first time doing this, there may be a pop-up saying that they want to access your camera. So you just click OK. So as you can see now, I'm not touching my face. They say I'm safe. And when I put my hands here, they also detect that I'm not touching my face. But once I touch my face, they tell me to keep my hands off the face. One hand is the same too. So this shows that my model is quite accurate in predicting whether I'm touching my face or not. Also, gentle reminder, remember to use the same environment when you're training in the Google Teachable Machine and now, because sometimes the lighting may affect your results.
Technically, we are overfitting the model, but in this case, because it's easier to use a smaller data set and train out the data that way. So yeah, it will be something that it will be sort of a give and take that we have to overfit the model in this case. But if you can try and get more data sets, and they'll be even better because you can use this model in anywhere, not just only your room or only at this angle or so on. Another thing is that you can consider implementing other JavaScript functions. So for example, you saw in the Don't Touch Your Face website that there was actually sound played and the elements changing. So because what we did was just an if-else code, and inside the if-else code, there's a lot of expansion that you can do, and there's a lot of features in in websites that you can make use of as well. So this is a good opportunity point that you can make use when making your prototype. Yeah. So essentially just put whatever you want to implement inside the if-else, and yeah, it should work.
When I turn my head, it shows that I'm not. Yeah, when I turn my head, they also say that I'm safe.
I mean, it's slightly inaccurate because our model was overfitted. So because she moved slightly away from the angle, so it will change slightly as well. Yeah, unfortunately, that's the case. That's why we want to encourage everyone to have a bigger data set and be able to train for all different kinds of circumstances.
We are not very sure on the implementation of Flask and Python, but I think maybe you can try out if you want to explore more about it.
I think Mr. Carl Waller is inside the Discord, so possibly he could help out and if your queries regarding code collab, because we are not too sure about that, unfortunately. Yeah, thank you.
I think as of now, Google's teachable machine, they would require you to have it's just a normal webcam, so it'll be your background and your face. But maybe to prevent the overfitting, you can take your video in different environments with different lighting conditions. Then maybe it will make the background less affecting the accuracy of the model.
Any last questions before we end off? Minjia, could you return to the slides? Thank you.
Okay. Yep, and last words, you can actually explore more about maybe not just saying you're safe or keep your hands off your face. Maybe you can be like the JS Don't Touch Your Face website and have some music effect. Yep, so that can be explored. Now going back to our slides. Yep, so thank you all for attending the Intro to ML, both sessions 1 and sessions 2. If you have like any questions, you can contact us via the Building Blocks Discord at 1YTLAM and at CSOE. Thank you.
Thank you. We hope you've learned more about the implementations and how you can use teachable machine model. If you have any questions, yeah, feel free to come forward. Thank you.
All right, thank you, Minjia and Ikling, for the wonderful workshop. So hope you all have learned something about teachable machine and what you can do with it for your prototype. Speaking of the prototype, we shall now head into the next section,
which is your AI win petition. You guys have 1 hour to work on whatever you guys, to work on your prototype. And let's not waste any time and let's get right into it.
For those who have submitted the 2359 submission yesterday, the feedback has been sent to your email. So please go and check it out. If not, you can move into your breakout rooms now.
Welcome back, everybody. I hope you guys had fun working on our project. And now we shall proceed with the second workshop of the day, which is Face Recognition with Python, Part 2 by Ansu and Andrea from Anglo-Chinese Junior College. This workshop will span over the course of 2 hours, and it will be a continuation of the same workshop from yesterday. Fun fact, in addition to face recognition, another area of biometric identification that's currently being actively worked on is gait recognition, which uses how you walk to determine who you are.
That sure is a fun fact. Now let's pass the time over to Enzo and Andrea.
Hello? Hello, can everyone hear me?
I can hear you.
Yes, we can hear you.
Me? Okay, nice. So welcome back. My name is Andrea, and today with me is Ansel, and we are from ACJC's Tech Council, and we're going to be continuing from yesterday's workshop on face recognition using Python. So just before anything, I want everyone in the workshop to be able to have these prerequisites. I'll put the link once more in the chat before anything else. Where's the chat?
If you're still having issues with the installation, open a ticket in Discord that we can help you with later.
Yeah. And before anything, I also just want to go over what we're going to be building today. So, at the end of this workshop, this session of the workshop, you'll be able to basically replicate our Python program that recognizes your face. So how it works is, you input a tolerance, usually 0.4 to 0.5 is like a good
No, we can't.
range. Oh, okay, because my video is on. Wait, give me a minute. Can you see it now? Oh, no. Okay, cool. So it should work. Nice. Okay. So basically it's detecting my face and recognizing me as Andrea. And usually if I do like a weird face, oh, okay, sometimes it detects me as a different face and then it'll like ask a prompt for like a new person. So this is basically what we're going to make today, and it can identify multiple faces at once. So if you have like family who wants to try out, you can try it out with them as well. Okay. So cool. So yesterday, we'll just recap on what we've done. We learned how to extract information from images and videos, basically the different parts of the face, as well as the encoding so that Python can read the files. And basically we learned how to detect and recognize faces from an image, i.e. get the encoding from an image and then compare it to other encodings, as well as from a video, and also create an interface, i.e. the rectangle around my face that you saw just now and the name at the bottom. So if you guys want, the code and other files from yesterday, I will be putting a link. Oh yeah, yeah, the link is also in the chat. And basically we're going to be building off from yesterday's code and trying to enhance it. So what we're going to be doing for the first part would be optimization, because every time we run the code, we have to make an encoding for every single image. And it would be a lot faster if we don't have to reuse the encode, like make new encodings every single time and just have the encodings saved in one place, right? So how do we do that? That's where pickling comes in. So pickling and managing directories to move our pickles around, and as well as threading, which will allow the various parts of our program, such as the text-to-speech, the video recognition, and the comparing of the faces, to run all together simultaneously without it feeling like very slow and laggy. So yeah, let's start off by starting with what is pickling in Python. So pickling is a Python module used for serializing and deserializing Python object structures. Basically, what that means is if you have an object in Python, like a Python list, a Python image, a Python class, it will convert it into something that can be saved off of Python, like a file. We usually call it a pickle file. And then that file can be converted back into Python by unpickling it without having to like recreate the file all over again. So the two basic methods we're going to learn is pickle.dump and pickle.load. So this is just a screenshot from the major code of like where pickling is used. Usually you'll see it in when we're making new encodings and like putting it in the new like storage for these encodings. And yeah, why we're using it is basically it will save data from anywhere and reload data from anywhere. So in the case of the encodings, we can save the encoding as a pickle file and then reload the encoding without having to like make a new encoding every single time you run our code, which will greatly reduce the amount of time, especially if we have a lot of images saved in our database. So we don't have to like run through everything all over again since it's all just saved there. So let's start off by learning how to use pickles. So, okay. We're gonna start off by just opening up your idle or whatever else you're using and creating a file. I'm going to save it within pickles just so my life is easier. And yeah, so the first thing we need to do is import the module of pickle. So for those who are faster, you can just copy the code like down below. But for those who want to go at a slower pace, you can like go along with me. So import pickle. And then just to show you guys how this works, I'm just gonna make any random object. So that some object for the example is a dictionary. I'm gonna make a list of random numbers and maybe a list inside a list with like words. Yeah, just so you can see, like it will work with any kind of object. And then basically how to do it is you need to assign a file and assign the file, and then the object you're going to be assigning that object to the new pickle file. So the way we do that is with open whatever name, I'll call it list dot pickle. Doesn't have to be the full word pickle. I use the short form because we can. And then WB stands for write in bytes, because pickle files are saved as a string of ones and zeros. So you need to put the B at the end for it to be able to be processed as a pickle file. We'll call it that. And basically, we're just going to use pickle.dump. And then the first thing that you put in the parentheses, the first argument, would be the object that you want. And then the next argument would be the name of the file that you want to put in. So this can actually be open whatever, but that's really like annoying. So pickle file. And then when we run this, okay, it ran. when we go into our folder for pickle, you can see it created this, this pickle file here, which is list.pkl. And just to show you that you can access this object from like any new program, not just within the same program, we make another file. And what am I doing? And we'll save this as retrieve pickle. So same thing. Okay. We import pickle, and then we open, I called it list.pickle, and we have to put in RB, which stands for read bytes. Make sure it's RB when you're loading a pickle, because if it's WB, it will overwrite the previous pickle that you just made and you're going to delete all the data. So be very careful about that. As pickle file. Pickle file. Then we can have the loaded object as pickle dot load pickle file. So just make sure that the pickle that you're trying to load is in the same directory as the Python file you are writing in. That's why I put everything in a folder called pickle, just so that I can explain it better and can retrieve everything, so it's neat. And then we can print. I'll just put loaded object because, yeah, just to see if everything is working. And yeah, see, you can see that even in another program, as long as it's within the same directory, we can load up whatever Python object that we made from the pickle file. So yeah, that's a really cool module that Python has that will be very useful for our encodings later on. Okay, and yeah, next is handling directories. So obviously, since we're making files out of the pickles, we need to know where to put these files. And since the encodings are of many different phases, we need to know how to create folders for a specific phase to create to store all the encodings so that we can retrieve them easily later on. So the basic things that we need to understand is we can handle directories using the OS module. And the main methods that we need are make directories, in short mkdir, and list directories, which basically returns all the folders and directories in your, wherever you're loading your Python file from as a list. Yeah, so we'll quickly try that out. Okay, so make sure you save your file in the correct place, because it will not load the correct things if it doesn't. So I'm going to put it in practices because there's a lot of like folders here and it will allow you to see in practice directory. So I'm going to call this directories. Oh, whoops. Whoops. I made a mistake. That's okay. But okay, whatever. Yep. Okay. So this part is very simple actually. Okay. First, we have to import OS like we did in the previous workshops, and then print OS dot list or LST. That is the real question. List the directories. And this should basically list the directories that you have in the folder. So see, we have a building blocks directories.py and do not remove. So, and the next thing that we have is make directories. It's basically, we make a new directory or a folder. So the way to do it is make directories, whatever new directory that you want, the title, and then I'm gonna print the directory again, just so you can see that it's changed and added this thing called new directory. Yeah, so see, it makes a new directory. That's basically it. And the last part that you will need to use later on when building the whole large program is shell utilities. So basically it's a Python module that has many functions, but what we are focusing on is a specific method called util.rmtree, which basically means remove tree, which deletes an entire directory tree. What does that mean? It means for, where are we? Okay, in this place called practice directory, if we go into new directory and then like, I don't know, add a folder and then add another folder inside. And then you have like a text file, text. And it will basically delete everything within new directory and all the folders. So that will be useful later when you're trying to debug your code, and then it'll just make so many copies of directories. Okay, so just to quickly test it out. We get, where was that? Okay, we go back to directories. We want this. No, we don't want this. We import shell utilities, util. We don't want to make a new directory. Instead, we want to remove that rm3. So what it should do is it deletes everything within new directory, even the files inside. Yeah, and that is about it with the basic understanding. And all we need to know is how to use dump, load, make, list, and remove. So before I move on to threading, we're going to take our code from yesterday and apply these things that we have just learned. Oh no. Oh no. Okay. So I believe, yes. This is where we left off yesterday. And if you guys don't have the files, I'm going to be pasting it in the chat. So these are the files that you basically need to work with. What's in the link that I just sent you is a from session 1. You'll have a known faces directory with images of Chris Pratt, and you'll also have the code that I'm working with right now, which is face recognition folder video. And just to show you what this does before we like work on it is this is the wrong one. Oh no. Let's go to is this the correct one? No, this is not the correct one. Yes, this is the correct one. Okay, cool. So what it does is basically, it will go through the known faces directory /name, basically the images of Chris Pratt that we have in known faces. And it will load the image and make an encoding of that image. Now, this is the part of the code that takes a lot of time, especially if you have a lot of images. And then, yeah, basically it will like append through the code and then compare the video feed with the current encodings and see which is the most similar and then say which is the most similar. But what we're focusing on for this part of the session is getting rid of this part and having a collection of encodings loaded up so that every single time we run it, we just load from these encodings. Okay, so yeah, let's start with this. Okay, let's go back to, I'm going to have the finished version at the bottom because I cannot remember the code from scratch. I will make a mistake. But at the same time, I will be working with the code that you guys have at the top window here. So you guys can follow along, but if some people prefer to go ahead, just look at the code at the bottom, and that's basically the whole new code thing. So before anything, we need to make a folder for where we want to put these encodings, and I would call that known encodings. Basically an empty folder where you want to put all the encodings. It can be named anything you want. And then, yeah, so to reference that directory, I would just make a simple variable known as encodings directory and label it with the name of whatever you have. Oh no. Yeah, so we'll also change the tolerance a little bit higher. So since we want to change this into something that will access the encodings itself, we don't need all of this. So I will comment it out. And then we're going to start with, wait. Processing the image file. Wait. Okay, wait. I realized that if we do this right away, we don't have encodings yet, and we need to make the encodings. So we're gonna start with a blank file to encode all the images into a set of encodings. Still in the place known as known encodings, you still need that folder. So sorry about that. Forgot we needed to do that first. Okay, cool. So what we're going to be making right now is this separate function called the encoder. In the final program, the encoder is within the large chunk of code itself because it takes from the video feed. But in our case, since we're making encodings from the images in the known faces directory, we need to have like a separate function that will create encodings of these images as they are. So how to do that is the first things we'll need are the modules face recognition, OS, Pickle, and CV2. Oh, do I need date time? Oh yeah, I need date time. Okay, and basically we'll need variables for encoding directory. This is just to, in case you want to change the name later, it's very easy to change and you don't need to go through so much code. Technically, you can put the name of the folder within the code itself, but then if you change the name, it's going to be a problem. So it's just good practice to have it saved as a variable. And then we don't need tolerance. Why do we have tolerance? Okay. So what we're going to do is go through all the images in the known faces directory. So in this step right now, we're going through known faces directory. And in mine, you'll have Andrea and Chris Pratt. So we're just going to print starting with name. This is just for troubleshooting later to make sure the code is working. It's not necessary, but it's very useful in when trying to debug later. So after this, we'll be going into name, right? And then in name, there's pictures. These are pictures of me. And these are pictures of Chris Pratt. So we want to iterate through each picture. So we'll type from picture in OS, this directory, and we're going to known faces directory, name, and this will bring us into the directory. Oh, this is the old version of the code. This will bring us into whatever pictures there are. And then again, just to make sure we know where we are, I'm going to put a print statement just to be safe. And we're going to load the image using face recognition, load image file, and the name of the picture in the item. So known faces directory name and picture. Okay, cool. So this will load the image, and then we need to make an encoding of the image through face recognition, face image 0. 0 is because the face encoding slowed as an array, as stated before, and you just need the first element in the array. So, okay. Now, after you have the encoding, you want to save this encoding as a pickle, right? So how to do that, like what we did before, is we open a file and we call that file encodings directory /name. So we want to save it in the encodings directory, right? Like in known encodings. But right now, known encodings is an empty folder. So you want to create a new folder to store the data for that specific image, for that specific person as well. That's where we have the make directories part. So you make a directory for every single face that will come in, and you just name it as whatever the face is. So encodings directory name, because name is a variable that will be the face. But then at the same time, you're going to run through this for every single picture. And if you keep making directories, you're going to have errors. So to prevent like file exist errors, we put a try except loop, which will easily bypass that. So So if there's no folder, it will make a folder. If there is a folder, then it doesn't need to make any new folder. It's already there. Yeah. So the next part is we need to name the pickle folder. So what we did to do that in the final program is, because in the final program, it's taking from the video feed and not from images that you have. So what we used is time as the ID for the photo. Technically, you don't need to use that now, but I'm still going to show it to you now, so it will be easier for you to understand in the future code. So honestly, you don't need name at the bottom. So to make an ID, we basically call it, it's called timestamp at the bottom. I want to call it ID because I can. Time.time. And it will basically give a ID of the time that it was made. Okay. And we save it as a pickle file. And remember, when saving pickle files, you need to use WD or write bytes as pickle file. Okay. And then simply save it in as pickle dump. The encoding, which is this thing, the object, encoding and pickle file. Okay, cool. So this should make encodings of every single face that is in the known faces directory. Okay, so when you run the module, it loads a face, loads a face. See, it takes a long time for the encoding to load. This is what we're trying to avoid. This Chris Pratt image is very big. And this one, I also believe is quite big, so it'll like take a while to load. Yeah, so now that it's done, we can see that in our, oh, I ran it in the wrong place. Okay, whatever, it's fine. In demo copy, you'd have like pickle files of the encodings that I ran twice. So going back to demo itself, let's run the actual encoder. Wait, no, let's just save this in the correct. Where did I? Okay, you know what, whatever, never mind. Yeah, okay, is this the same thing? No, this is what I was looking for. Whoops. We'll save it in the correct folder. I am sorry. We save it in encoder demo. There we go. So non-encoding's empty now, right? When we run this, it should have the pickle files of the encodings. Okay, promising. Okay, great. Also, if you run it twice, you get 2 copies of the encodings, just so you know. But it shouldn't run an error if you run it twice. You just get more encodings. So we should have folders of Andrea, which is the encodings for the pictures, and Krista, which is the encodings for the 3 pictures and 4 pictures respectively in this folder and this folder. Cool. So now that we have the encodings done, we can finally work on enhancing the code that I was talking about. So if everyone can open their face recognition folder video.py or whatever code they had from previous, and just comment out the whole chunk of processing the images with known face, because we already did that in our encoder program. Let me just make sure I'm working in the right folder again. I'll just save you in the right folder later. Okay. So we need to start off by importing the things that we need to make it work. So we need to import pickle. And everything else has already been imported in the previous example. So now we need, instead of processing the image files, we're processing encodings. And basically, we just need to access the encodings folder by going to encodings directory, which we will create as a variable for our folder as known encodings. And I'll just copy this. This is basically just to see that we're in the right place. And go into the files. Encodings directory and slash name. Okay, so right now this loop would be in encodings and that thing. So we need to process all these things or just get the data from these things. And how to do that is we would just have to, okay, let me just put this real quick. Okay. We would open the file, of course, and the file would be in your encodings directory, name, and file name, or whatever it is your iterator is. And remember, when you're loading the encodings, it needs to be RB, read bytes, not write bytes, because you don't want to overwrite the encodings that you already have. And then I don't need to print the text. Then your encoding would be pickle.load pickle file. And that's basically it. So instead of loading the image and then going through the whole thing again, we're just loading pickle files. And this is this part is from the previous code. We'll just append it to the known encodings list at the top and the known names list. And then the rest of the code runs basically the same. It's just now it's faster. Oh, yeah, see, like instead of like the long waiting time we did for that. Oh, yes, my video is on. Let me test that again. Yeah, so it loads much faster now because all the encodings are like preloaded within the encoding file. So that's basically it. Okay, Q to close the window, yes. Okay. And I hope everyone understood that part. And before we go into the next part, I just want to introduce to you the concept of threading. It's very simple, like one line to add into the code that makes everything run together without us like waiting for things to load. We have all these like modules, but the only thing that you need to know is from threading, we import thread. And what is this thread? It's basically their own system levels that are, think of them as windows. So within your program, you'll just have like many windows like on running at the same time. So a thread can like run independently within its own thing. And how this is used in our face recognition program is in the text to speech. So when we're running the program, it will prompt you to say like, oh, hi, how are you? Who are you? But then when that happens without threading, the video will pause. And we don't want that to happen. We want the video to keep getting input, even if the window asking for who this image is to identify it is still running. So before the break, I'll just show you how that works. I'll just like delete my face from the thing. And okay, what am I looking for? I want to share the sound so you guys can hear it. By the way, guys, a tolerance of 0.4 to 0.5 is the best through our trial and error, because like otherwise it. Oh,
hello, who are
where is
you?
it? Where is it? Yes, that's the one. It will ask for your face while the video is still on.
Hello there. Andrea.
Yeah, so it's
You
still
look
talking
familiar.
while it can see my face. Yeah, that's basically it. So okay, yeah. So before we jump into programming the whole thing, I'm going to give like a quick 5-minute break for you guys to just rest. And when we're back, Ansel will be taking forward and helping you code the program, the whole program properly.
Alright, it's 11:34. I'll be bringing everyone through how to assemble the final product. Start sharing. Alright, so first I'll be dumping a hold on, sorry. I'll be dumping a whole bunch of imports into the chat. I'll just send it all at once first so that we can use it later. I'll explain how we're going to be using each one as we go. So first we have this. So first things first, we shall be going through the text-to-speech, setting it up so we can use it later on. To do that, we need to initialize engine as ByteDance.init. Is this better? Okay, and then we define a function that we're going to be passing into so that we can call the text-to-speech with engine.say text, and then engine. run, and wait. Then we return because of the function to close the function. So what this will do is takes in the parameter text and then passes it into the text-to-speech engine and runs and saves it until completion. Oh yeah, all the codes, both this basic version and the optimized version, which I will be putting together later on, will be uploaded to the same folder as all the other codes. Okay, so now we will have the encodings directory and fixed directory, same as the other demonstrations based on folder video and folder image. And then we're going to be setting this variable called tolerance, which we'll be using. Let me adjust something in my audio. Okay, so the tolerance will be used later on to determine how accurate we want our our program to be. It'll be from 0 to 1.0. The lower it is, the more confident the program is that it's the image. So if we set the threshold to be 0.4, maybe it will be more consistent but less accurate than a 0.2 maybe. Then going to initialize some more variables like frame thickness and font thickness, which we'll be using for drawing the box later. Once again, it's similar to the folder video and image. You can copy a lot of these initializing variables from there. The main difference will be this here, PTS counter and PTS list, which we'll be using as part of the loop as an extra bit of things, so it adds variety to the text-to-speech dialog. Then we're going to need to initialize all the different faces that we have stored already. So for name, os.lister, encodings, the print, starting with name, just a bit more extra printing so you know what's going on in the program. Then for file name, and os.lister, then we're going to use a f string again so that we can add a name to encodings there. And then open the subfolder name. From there, we will be loading file name. And then, so now we are iterating through the encodings there, and we're getting the each file from it. And then we'll be using pickle to open up and read the encoding file, which we have stored just like in Andrea's demonstration, and then storing it temporarily in encoding. If at any point I'm going too fast, just send a message in chat to let me know. So now we've got the encoding and we've got the name of the person. So we store it inside known faces and store it inside. So the name inside known names. So this way, for every file that we saw, maybe we are adding one dot pickle. The actual encoding doesn't look like that, isn't like that, but it's just for demonstration sake. So this way, known names will align with the known faces pickle. Well, because we're appending a name to each encoding that we're storing. Say, for example, these two are both pickles of encodings of my name, of my face. Then from there, we will be storing next ID as the length of known faces, which we will be using next ID to store new faces that we're adding into the program every time it detects an unknown face. So this way we can prevent any conflicts, like maybe something went wrong with the saving and it didn't save under the name, but instead under next ID. If we use next ID, then no names plus one, it won't have any clashes regardless. So another variable we're going to be using later again, copied list. We're just going to spell as an empty list. So now on to the actual meat of the program. We have video equals to cv2.video capture. 0. This will take the webcam that I am currently using in Zoom. I'll have to disable it later. And we'll have this colors, which is using a dictionary. Later on, we'll be using it to store what color the box to be drawn around each person's face will be. And then the main loop, while true, since we want it to run as long as possible. We grab the frame, and then we flip it so that it's properly mirrored. If not, you move left, the video will move right, and so on. We take the second index of video.read, which will give us the actual frame itself, passing it to cv2.flip with the one flag to denote the flipping it horizontally. Then, using the face recognition library, we take locations, goes to face recognition, face locations, image. This will give us a list of face locations in the order of top right, bottom left of the box that is to be drawn. So then we have the position of where the locations are, and then we can work with that to determine who it is. So now we look through for face locations. We take each location that each face that we have found, and then we take the encoding of it. So this will be the source frame, source image taken from a frame of cv2.video capture. Then we are going to only pass in one location, which is face location. And then since it returns a list, of one element we take the 0th position to take the encoding that we want. From there, we are going to take the results to be face recognition dot face distance. We have the known faces list, which is the what encodings we have stored previously, what encodings we have found. So this will be the list of encodings to compare to. And then our face encoding. Is the bracket. Okay, so in the event that we are running a brand new instance of it, so we've got no encoding stored, we've got no faces stored, it's seen nothing, no face, results will be an empty list because it's going to return a list of the same length as known faces, returning a list of confidences. So this will return a list of confidences of how similar the encoding is. With the lower the confidence is, the more confident the program is that it's the same face. So if we have no faces compared to, it can't return any confidences. So first we need to check if results is greater than 0. So that means we've got something inside results. Then we take the closest to be min results. This will give us the most likely face that it's going to be, most likely encoding is going to be. And then if we have no results in the list, then we just store it, put it as one. Since our tolerance is set to be from 0 to 1, 1 will always be greater than any tolerance that we provided. So the later code that will be used to check if it's a face we know will always fail. My bad, maybe I shouldn't call it confidence, it's you can call it distance of numbers of how different the encoding is from the encodings stored. So now that we've gotten what is the closest face that we have, closest face that we have stored compared to the face that we are seeing right now, we can use that to check if we know the face. So first we need to check if it's a valid face. where tolerance would dictate how confident we are that it's how far it is from the faces we have stored. The limit upper limit of what we allow to be considered the same face. Then we, just like in the previous demos yesterday, match equals to known names results.index closest. So this will give us the name that is aligning, just like in here. So we have results maybe 0.0 and these are just arbitrary numbers for a reference. And then if the tolerance 0.45, then results 0.123 whatever, this will be closest, and 0.813223, even if it ends up as closest somehow, it will be rejected because it's greater than tolerance. So now that 0.1, we have this from results stored inside closest, then we know that it's aligned with Ansel, and match will be then the Ansel. From there, we can first say what we want from it, pass it into text-to-speech and greet the person. So we can use this. So what this will do is it replaces any underscores that you might have put in the name with a space for text-to-speech if not get messed up. Say hello to the person. And then add in an extra greeting, something like nice to meet you, you look familiar. You can add whatever you want using random.choice, which will take a random option from this list that is provided here. This list, if I make it say just A, it might pick, there's a 1 in 4 chance of picking A. Okay, from there, so right now we have a program that can first load all the previous encodings that we have, and then takes in the video stream from CV2, from your webcam, and then if it detects someone it recognizes, and the tolerance is, the closeness is below the tolerance, which means it's valid, it'll greet the person. So now we are going to handle what if it doesn't recognize. So the closest closeness that we have gotten in results this year is not close enough. It's not a valid enough number since it's greater than tolerance. Greater than or equal to tolerance, then that means it's a brand new face. So first we store match to be string next ID. This will be a temporary name that will be storing the image and the encoding tool, both for the folder and the file name. Then we increment next ID by 1, since we have a new image being added, new person being added, sorry. Then no names dot append match. This will let us have a name at least assigned to the encoding in case something goes wrong later on in the storing of the actual name. And then we have the index to be no names dot index match. You could also do known names equals to len. Oops, sorry. Index known names -1. So this will give us the index of the last item in the known names list. Then we will append the encoding. Face encoding. So this will store everything into this format. This format again, just this will be a temporary variable of maybe temporary number of maybe 12, and then the numpy array encoding. So I'll just call 3 now. Because we will be saving it to the pickle file. So first we os.migder. We'll be making the directory where we will be storing the image, the encoding to. And just in case the directory somehow already exists due to the match not properly initializing, we'll use try except, which will catch any errors. Try will catch any errors that might occur in this body of code here, and then skip directly to accept and just pass. So that means the directory already exists. We don't need to create another one with the same name. Then we make timestamp to be datetime .utc now timestamp. This will give us the time right now as a timestamp, so we get a unique string in here that won't clash with any other previous one because time has passed since the last instance, and the timestamp will be different. This also includes the date and year. That's why it won't clash no matter what day you do it on. All right, then we create and dump it into a pickle file. So using pickle, again, we put the face encoding into pickle file with match being the stringified mix ID and timestamp. So we have a unique file name pickle. And then from there, so first, right now, we will have the encoding stored in a pickle file. We'll have it stored in, say, maybe 13. And then we will have maybe 13 timestamp. So then it'll be something like this stored right now. Next, we're going to be taking the image that we're going to be storing. So by right, the program doesn't actually need this image, but it's so that we have reference for maybe we want to do some debugging of maybe the wrong name was stored to the wrong person. We can then reference this directory. This directory right here. so that we can see who was the image saved to. So what name was the image saved to, and the encoding that is paired to it. So you get the 4 dimensions, 4 positions, sorry. From the face location tuple, face location is in this, since it's in this format, for as mentioned earlier. So now we can get the sub image of the frame of the video stream. So image in this case will be the frame, and we're taking this sub image from it. Then we store it under the image file name. Make sure that this this part here is exactly the same as this, because it's the directory we're saving it to. And then we store it under the name match timestamp again, just like the pickle file. So this way you can compare it directly with the stuff in the encodings directory. Make sure that you have this .png extension at the end. You can probably use JPEG as well. Is to make sure that PIL, which is the Python image library, can save it properly. So this will take this image file, oops, sorry, my bad, I missed out something. So image equals to image, no, from array face image. So this creates a PIL, which is Python image library, image class from the NumPy array that is the sub-image of the current frame that we're looking at, and stores it inside PIL image. Then we save it to the image file file extension. Okay, sorry, my bad. JPEG doesn't work. This must be PNG. Okay, so now that we've saved both in temporary files as match timestamp, we're going to need to query the person for what's the actual name. So text to speech again. So this will ask, who are you? And then using another library called PySimpleGUI, this will create a pop-up, just like in maybe when you're saving a file on a browser, there'll be that pop-up that will query you on where you're going to save it to. This will be something like that. It's just a text field only, and then it will show also the image that you're checking, and using this here, image equals the image file. So now that we have stored, and then it'll pass whatever you type into the text field, the name. Now that you've got the name of the person, we will be passing it into we'll be storing, sorry, not passing, we'll be storing it properly. So for encoding in OS dot this there. So this will be just in case you have more than one encoding stored within that under that same match, because they didn't go up, they didn't increment a bit more. Then let me see if I can. Okay, there. Okay, so first we check is name empty. This will happen if you just close the pop-up. Sorry, if you don't put anything and just press enter. Or name is none. This will happen if you just close the pop-up. Or if you can put it as an option to type a letter to delete the image. So this will make sure that you don't save it. You don't save an image that you don't want. We use shootil.rm3 to remove both the encoding directory and the pictures directory. Then we pop the last element of known faces and known names, so that we won't have so that we can properly delete it from both the stored files and what the program is working with. Now, if we actually got a name, we add it into copied list, which we have initialized all the way in the beginning. Where do we go? Here. And then we make a proper directory which will be storing for the names. So now this will be the more permanent directories that will be storing the names as the folder. So it look something more like this. And then we'll be now copying this into here and storing it under a proper name. So we have this, copying the file into there, using the encoding as the file name instead. And then now we'll be copying the picture that we have stored into the same pictures directory. So now we'll be replacing the known name text, which we have taken from here. and then replacing it with our name. So this takes, okay. So this will make it such that no name and Andrea. Will now be like this. If it was previously, let's restart it again. So this will replace the index with this and give our program the right thing to work with. And then just as a bit of helpful output so you know what's going on, we print done. Outside of all this stuff under the else indent. So this lets us know that it stored the encoding and the picture in the right directory, whether it's it handled the encoding file, pickle file, and the picture file that you're storing, whether you're storing it under a name or you're deleting it because it's an invalid one. Here is a picture that you want to delete. And just to be safe, we're going to be removing all instances of match, which will be still under next ID. And this will try to remove any of the temporary folders and files that we created. Okay, so right now we have created actually most of the base of it. This will be able to recognize, and if it doesn't recognize a new person, if it doesn't recognize the face, it will store it as a new person. And we are mostly done. All that's left is to draw the box around the person using cv2.rectangle and cv2.flex. So we can have an actual label to the person's name. So outside of all this, we have it under check with try. So we have initialized colors as a dictionary earlier on, and we check if we have so this will check if the match is inside the colors dictionary, then we can take the color directly from it. Otherwise, we take color to be random.choice. I'll be copy pasting this into the chat as well. These are a bunch of RGB codes. You can actually put whatever you want, but these are the primary colors like red, green, blue. I think this is light blue. This is purple, I think. I don't remember. For those who are having issues seeing, this file is in the inside the folder with all the other resources under the name BBCS Basic. And it should be pretty much the same, just the comments might be different. Okay, so we assign color to be a random color from this list that we have here. And then we store it inside colors for future use. So this will make sure that any time we've started the program, when we have one face, we'll have a color assigned it. So maybe my face will be assigned red, and for the rest of the duration of this, duration of this running of the program, my face, the box drawn around my face will always be red. Maybe in a future one, it might end up as green, but for that instance, it will always be green. Then we take the location of the sub image again. So this will be the location of my face. And then we use this text which I'll paste in the chat to draw the box. So this will draw a first a rectangle that is not filled, but it's just a empty picture, like a picture frame from left to top and right to bottom of color from here. In this image, frame thickness has been initialized all the way at the top here. And then a second box right below the original one with the +22. And this will be a filled one instead. Same color, same location. Like that, it should be. So it should be like this. Bottom is correct. And then it puts the text onto it. Did I? No. Colors has been is a diction. It's not a list. It's a dictionary, which is key value pairs. So maybe it will be something like color. Like this. And then this, so that the so Python knows when I pass in ansel into this here, it'll give me this value assigned to color instead. So then this will be to put the text onto this lower box here. And then this will give us a frame around the face with the name as the bottom part of it. Okay. Finally, we just need to CV through intro to properly display it, and then the essential CV2 wait key 1. So for a bit of functionality, I'm going to be using this wait key as well to be this, and use it so that I can quit out of the program video. So I video the release. I no longer take input from my webcam, and then cv2.destroy all windows, which will close any open cv2 windows that we have and break the end of the program. So right now, this right here is the most basic of the program. We have the loading of past faces and the encoding. Then we have identification of the locations of the image in our frame. And for each location that we have, we encode the that specific smaller image so it's faster. And then we check the closeness of the image to what we have stored at the closest value, and then we find the name that is associated with it, greet the person, and then if we haven't found anyone that we know, we will instead create temporary folders and files to store our encoding and naming. We query the person for the name, and then we store it. We properly assign the name to the files that we have stored down here. Finally, we clean up all the stuff, and then draw a box around each location. This is regardless of if it's a previously recognized space or a brand new one, since we have match to be assigned to the name, or match is already assigned to the person that is recognized as, and then we draw the boxes around it. Finally, we show it. However, if I run this, it is pretty. Oops. Oh, okay. Let me just run the working one. What? Okay, hold on. In case I can't get it working, basically the issue is that it's very laggy. Let's see. Yes, it's because I those demonstrating files. Oh boy, I think my delib is messed up. Okay. So Kim-Ning, do you mind demonstrating or Andrea, whoever is available, could you demonstrate BBCS basic? I'll keep talking while you set it up. So the issue is that it's very laggy. Because it's checking every single frame for if it recognizes the person. So what we can do is a few optimizations. So firstly, also another issue is that the text-to-speech, because of the run and wait, will interrupt the process every time, interrupt the program and freeze the frame in order to finish saying it. And we also can't do away with this. If not, it won't say the text at all. So what we can do is we can use threading. Okay, so sorry to interrupt myself, but Kim-Ning will be demonstrating my name, but it's a bit laggy.
Hi guys. Just quick change of screen. Oh, I'm not co-host. I can't share.
Okay.
And so I think you need end your screen first.
Oh, okay. I'll stop sharing.
Okay, yeah, can. Okay, that's really messy, but
Hello there. Kinman. You look familiar. Hello.
Super
as
framey.
you can see, it works. This is basically a copy of whatever answer just did just now. It's the identical copy. And this pop-up is from PySimpleGui. And yeah, I can type in my name. Oh, and it cannot create because I already have a folder called Kinming earlier on, because this was not the first time I ran it. But yeah, as you can see, it works. It detects me and with the color green. And if I run this program again, hopefully it doesn't crash because of the file just now.
We just leave it under a different name temporarily.
Hello there. 6. You look familiar.
Okay, I think I failed to name the encoding just now, so it assigned the number to it, which was the ID, which was 6. So now I'm 6. Yeah, and yeah.
And
So yeah, that's the demo.
framing. The FPS is really low. So we can add in a few optimization. First, we'll be using threading to deal with the issue of the text-to-speech. Then, so we're going to be using a two separate functions instead now. And it's like this. So first, we take release say to be the same, taking in the text, but instead we will be using, sorry, we also need this. We'll be using global variables for engine, run, and speech, so that I can access it between the two different functions. And then we're also going to need like this. So a queue works like a real life queue. You enter from the back and then you exit from the front. So when I use put, the exit to the back of the queue, and when I use get, takes it from the front of the queue. So first I check if run, this flag here, is false. It's true, sorry. That means that it's not looking through the queue at all. Then I start a new thread with this text-to-speech TTS function and go through the queue, getting the all the different text that needs to be set, and then run and wait. So this will run parallel to the actual program and won't interrupt it, and we'll be able to say all the text that I need to. So another thing that we can use, another optimization, which is this one is the biggest one, is instead of checking every single frame if we are for the same person, what we can do instead is if we have a face location that is within 20 pixels of the previous location, of a previous location that has been detected, then it's safe to assume that that person is the same. So for that, we're going to need a couple new variables, previous location and previous matches index. And then also current matches and current locations and current matches index, which needs to be refreshed at the start of every overall loop, every frame. So from there, we'll be looking through the previous location instead. We take the location 0, the 0th location minus left, which because previous locations will be empty on the first run through, left will may be empty, but once you run for at least one frame, left will be stored as here. So then just do it in Keynote. So left less than 20. So check if it's within 20 pixels, whether it's left or right of it. And so check vertically top or bottom if it's within 20 pixels. If it is, that means we can assume safely that by proximity is the same person. Then we set match to be known name previous matches index. So this will store a list of indexes of the names that we have. So maybe it could be so previous matches index would be something like 0, 5, 2, 3. Assuming that we have 4 items within the 4 faces that we have previously identified, and then these would be the location and names that we have to find, and then counter, which wait, sorry, no, my bad. Do this as well under here. So we have results, which is an empty list to be used later. We have match, just initializing it as none first. And when you take top and left to be face location. Oops, I'm so sorry. All this should be under face location loop. It should be like this. And then this that I just copy pasted in here. So that's why we have the counter for counter from, and then it will be used to determine which of these that we're looking at. So first will be 0, we're looking at, it might be the 0th location from previous location. Otherwise, we move on. Sorry, no, if it is, then we set found flag to be true. That means that we found it based on proximity, and then we append current location to current location and current matches index. This move left comma top, and then the same index that we found earlier. So if counter is 0, we'll be appending 0. Again, if counter is 1, we're appending 2, so on. So this will let us store the current set of images that we have found based on proximity first into current location and current matches index so that we can see it, so that we can use it for the next set of next iteration, next frame. Then we just can take the same talking stuff and then put it there and then say it. Since we've already found it, then we can break out from this previous locations loop and then continue on. Otherwise, we increment the counter by 1. So we move on to the next of the previous locations and previous match index. So now that we checked the base on proximity, we don't want to have to check and encode everything again. So we take all this up to the colors part, indented by 1. If you're using idle, you can control right square bracket. I'm not sure what you use for Jupyter, but you indent everything from face encoding equals face recognition dot face encodings by 1 tab, and then put it all under a if condition if found flag equals to false. So this means that you only encode, you only compare and everything if and only if you didn't manage to find it by proximity. And And then in addition, you're going to need to add in current whenever you find a face that you recognize from under here, where you have a match. You store it in current locations in current matches index so that we can use it once again for the next frame. Do it again for the new picture, all the way under here, where you've assigned the no-names index to be named. Once again, but instead of results.index process, we use index directly since we've gotten the index here. Finally, we're going to need to refresh previous locations to be the same as the store the current locations and current matches index to be previous locations, so we have something to refer to on the next frame. As current locations and current matches index will be overwritten by the information from that new frame. So this way we can compare frame 1, which will be the previous location and previous matches index, with frame 2, which will be current locations and current matches index, and the present frame. So this is one of the more dramatic improvements. And the last, which will be a slight improvement, both to speed and to accuracy, is using CVLib, which is an alternate face detection, not face recognition, just detection library import faces. In the installation prerequisites, we put it under optional as it's a bit finicky to install, just like BLib. It's so you don't necessarily need to use it, but if you're interested in making it more accurate and better, you might want to take the time to install it. We will help as well under the Discord. Then so we would replace the detect face locations here with locations goes to detect face. Sorry, detect face, not detect faces. Image. We will return a list of tuples. Which is again another set of tuples of the locations. And then the confidences, which is more like closeness as well. Just like the, sorry, no, this one is confidence properly, where one is fully confident that it's a face. Since we don't need the confidence that it's a face, we just need the locations, we can take the 0th index. So it's just the tuple of locations. And because CVLib stores it slightly differently from the face locations library, we're going to need to reassign it to be so we have I1, I2, so this will give us a tuple of the correct top, right, bottom, left order, because CVLib gives left, top, right, bottom, state. And then, so we reorder it using list comprehension, which will take each item from within locations and then assign it to rearrange it to be like this. So now we have it as the proper top right, bottom left order. And yeah, that's pretty much the overall optimized solution. There are other optimizations that you can make if you can think of. I am still working on another one that is still not, I couldn't get it working. Basically, you take the let me just add in a comment for anyone who wants to try it out. You take, and while you are comparing by proximity, it does speed it up. If you create a lot of different face pictures and codings from storing a whole lot of different people, then it's going to also take some time to compare. So what I was trying to do is when I detected a face, so instead of storing known names and known faces as two separate lists, I put them together as a dictionary of key name and then the value is a list of encodings. This way I can, once I detected a face, I can pop it out from the dictionary and store it as a backup. So that I don't need to compare for the next phase whether it's that person, since you already know it's recognized. Unfortunately, there's some, you need to work with the order of things. It's a bit finicky. Like when you put it and take it out from the dictionary, the order of the encodings within current matches index will also be messed up because the index of it won't be the same as in the list. So on, it's a bit more complex than I still haven't figured out. And then, so for this face recognition stuff, in terms of applications, you can use it for maybe you can use it for attendance taking. If you're in your CCA, you can set up a camera near the door. So people just need to walk in, maybe pause a bit so the camera can recognize the face. And then you don't need to have a go through and check if Tom is here, if Jack is here, you can just automatically do it. Or maybe you can use it to identify. Nowadays, it's no longer as relevant because we have online booking, but if you want to query the teacher in school, you can set it up at the PA system and then it'll scan your face, see who it is, and automatically, and then you just need to input who is the teacher you're looking for, and they'll automatically say the PA, maybe Ansel is looking for Mr. Teo. And then Kim-Ming will now demonstrate the improvements made. And so I'll be honest, I'm not sure how visible it'll be over Zoom. There should be an improvement though.
It should be. Can you see my screen?
Yeah, it's visible now.
All right. So this is the optimized code. No such file. What?
Oops, I guess I'll re-upload later. I guess I forgot a curly bracket. It should be under initialization.
What?
Should be under initialization file name, yeah. So curly bracket.
Initialization.
Further down when you're loading the encodings. And
Well, I just ran this just now. It worked.
because you didn't have any encodings, go to the font name in os.list the encodings there.
Hello,
It
who are
works
you?
now.
Yeah, it works now. What? Oh, that is because there was some residue from the last. Yeah, let's just delete all this. Okay, it should work now. The error was due to the folder Kinming already exists in known Facebook, but I did not delete it just now.
Hello, who are you?
Yeah, assigns me as ID1, and now I call myself Kinming.
Hello
Yep.
there. Kinmen.
As you can see, it's much smoother. And yeah, is there?
Oh yeah, also for the face locations function in the face recognition library, it has issues detecting a face if you have a mask on, but if you have
Oh yeah,
do you have a mask on? Yeah.
yeah, I do.
CVLib can still
Hello,
be able to
who are you?
recognize as long as you CVLib should be able to recognize your face, detect your face even if the mask on. Okay, I think I'll change it in the upload as well, and
Yeah.
you need to put the os.makedir under creating a new one with when you have it as a name under a try except.
Alright, but it's
Just like the just like when you're making a directory, the temporary directory where you have the try except around it, you're going to need to put a try except around the one where you put in once you've input a name. Do you have any questions? In order to make it so that we don't need to install Python and everything, you can use a I've forgotten what's there's another Python library that you can install to compile it. I think it's Py2exe, where it allows you to compile after you supply all the relevant directories, all the PyInstaller. Either PyInstaller or Py2exe, both can work. You can use it to include. Oh right, installer won't work on mobile. For that, okay, sorry, let me finish. Py2exe or PyInstaller lets you create an exe file that you can send out for Windows laptops. And I believe you can also compile for Linux if there's the rare person that uses it. For mobile, this one I'm working on and trying to figure out, but you can use opencv.js to create an Flask or some other web server to create a website that lets you run OpenCV on it and then run the face recognition in the background in the Flask server. It will be slower, but face recognition should still be possible on the website. Any other questions? If not, I believe our time is up soon. Can you remember what time we end?
I think
Oh, okay, it's lunchtime. So
okay. Anyway, thank you so much to the speakers for a wonderful workshop today. So thanks for creating the program that can help us like recognize our face and everything. So now with that program, I can finally say that I have a friend.
No, I do not want to be your friend. You are a terrible person and nobody likes you.
Oh, okay. Anyway, now we shall go into the next portion, which is going to be lunchtime. So please get back by 1:45 and we will resume the next part of the workshop. I think they will also be opening the breakout rooms for those who want to continue working on the prototype. So if you want to continue working on the prototype, you can, yeah, okay.
All right, hello guys, and welcome back. I think now the time is about 1:45, and let's continue with the rest of the programs. The next workshop that you guys will be having is Music with AI by Rose from Dunman High School. This workshop will take place over the course of the next 2 hours.
Sorry. I'm glad that this workshop happens because I think she's gonna teach us how to make more music using AI, as the name suggests. And that is really good because nowadays modern artists take so long to make music that I have to find more artists to make I have to find other artists to listen to while the artist that I'm trying to listen to is making music. And they just don't sound the same. I have to keep finding new artists and more artists, and then
Anyways, let's welcome Rose.
Hello, can everyone hear me?
Yep, we can.
Okay, thanks. So hello everyone, welcome to Music with AI. And so first and foremost, I want you to listen to this piece of music. Wait, let me actually restart. Hopefully there's audio. Can you guys hear it?
yeah, we can hear it.
Okay, yep. All right, so hearing from the song, right, we can deduce that it's actually a D flat major. Hopefully I got that right. And most of the time when you ask people how does it make them feel, most of them will say they feel relaxed or nostalgic. It has a lot of rubato, which is like the flexibility or the pause in the performance. And it speeds up and slows down, like if you hear the whole song. And so people might think that it's difficult to capture the rhythm. So all these illustrate how difficult it is to have a program to tell it to have a rubato or D flat major, to be classical, or to have a male vocal. So all these seems human traits or attributes that is unique to us and impossible for computers to intuitively know and how to apply it properly. And such things are tackled in music information retrieval, or MIR for short. So what does MIR encompasses? First of all is fingerprinting. Is this work done by a particular artist? There's cover sound detection. There's genre recognition. Transcription, getting information such as the start time, its duration, its instrument label, and its loudness. recommendation of a song that are similar to the current taste of music that you currently have. Mood, or MER, which is, it tells you whether is the song nostalgic, happy, upbeat, sad. Instrument recognition, is there a piano? Is there a drum? Is there a viola? Is there a vocal? Score alignment. So if you have a musical sheet in front of you, it will actually be great to have a red cursor that highlights the notes that's currently being played at the moment, like while you're listening to the song, right? Because sometimes you don't realize it just by merely listening to it. So maybe having that visual aid allows you to have greater intuition of the song. Tempo estimation, is it 60 beats per minute, 80 or 120? Key detection, is it C major, D major, or B flat major? There's also beat tracking, query by humming, and many, many more. So, sorry. Today, actually, quite a lot of applications of MIR, right? And it ranges from, sorry, it ranges from YouTube, such as copyright detection, Google and Spotify for music recommendation, and other music analysis software companies. And you'll notice that in the Python files later on, these three main steps are going to be applied repeatedly, and they form the basic fundamentals of MIR. So from uploading the audio to segmenting it to different parts, standardizing it to a specific frame size, and allows us to extract the features, followed by a notion of machine learning, and then we can obtain the musical information. So sounds are basically fluctuations in the air pressure. And hearing a sound means that signals of those fluctuations are sent to your brain for further processing, which is what MIR wants to emulate. And this is one way in which we can segment the data, which is just basic time analysis, where you segment it per second. Oops. So if you look at it more closely, you realize that some parts of the wave front or the segmented audio is really cut in between the notes, which is quite weird if you want to extract its features. It's like half a note's being played, but you want to actually know like the exact full length of the note. That's why we mostly rely on set segmentation, which is cutting it per major change in the pitch, right? So you can see that at the start of each note, there's a major change in the wave plot that's being formed. So this is the most preferred way of segmenting data. And after choosing the framing strategy, we want to do a feature extraction. For instance, the zero crossing rate. So it is a simple time to mean feature. Technically, it's the number of times that per unit time that the signal crosses the x-axis. So you can see that the yellow dots highlights the time that it crosses the x-axis. And in this case, for frame 1, there's a zero crossing rate of 9. So comparing frame 1 with the next frame, frame 2, we can safely agree that frame 1 has a lower zero crossing rate than frame 2. Another way to approach is looking at the frequency content and parameterize the overall spectrum. So maybe we can get the centroid or the spectral mean, which is the average frequency content of the audio, aka like the brightness or darkness of the sound or the volume. It's not exactly about the pitch content, but rather the entire song where multiple pitches are present. So it's the mean or the average pitch for a particular segment. Or we can also look at the spectral spread or the spectral slope. So once we're done segmenting the data and extracting its features, we can move on to classification. And we can classify them according to the purpose of our algorithm. So we were using a scikit-learn library for this workshop. And this is the basic structure of it. So you can see that despite using any of the 7 classifiers that I listed in here, it always leads down to model.fit and model.train, especially for supervised learning, where you need to train your algorithm based on a training data set and test it based on the testing data set. So this generic flow or frame allows you to actually easily swap amongst the different classifiers and use the optimal one depending on your situation. So let's look at some code. I will paste the link at the chat. Yep, so this is what you'll see when you click on the link. All of them are pre-filled, so there's no live coding involved. Okay, so the first part of this coding session is basically extracting audio features. So first of all, we have to detect onsets because that's where we'll segment the audio and compute the features for each segment. And then we can gain the features by listening to each segment differently. So in a sense, like what does each segment or feature actually means? I have no idea why it's running so slow. Yeah, okay, it's done. All right, so now first step is of course retrieving the audio. So what I'll be using is this urllib.request, and this is the URL that I found. And then, wait, let me just run it. So it will actually save it as simple loop.wave in our machine. Right, and then we will use this attribute called librosa.load. And it will actually save it into this variable called x. So it's going to turn it into an array, right, and save it in this variable x. And then SR actually shows the sample rate. Right, so the sample rate in this case is about 22 kilohertz. So what's sample rate? Basically, the lower sample rate you have. Oh, you couldn't catch what needs to be downloaded and installed. Just look at the link that I sent. Right. Basically, just open the IPY and B files, and then you should have all these things written on it. Yeah, I know. Right. Yeah. So, in this case, we have 1 kilohertz of data, right? And what we want to do is actually record the maxima and the minima. That's why the sample rate is going to be twice of that of your audio signal. Right. And in a human hearing, it's about 20 to 20,000 hertz. That's why you need a minimum sample rate of at least 40 kilohertz. And most music softwares have a sample rate of 44.1 kilohertz, right? So as to not dampen the audio quality or the timbre. Right, and then we'll use IPD the audio, right? We'll put in the file name and then the sample rate of the original file that we have. And this is the song. So it's a lot of drums and all. So this is going to be the wave plot. Right, so you can see that the different onsets that we have. And we'll actually compute the short time Fourier transform. So if you want to learn more information, just click on the links that will direct you to the sources that I've based it on. But essentially, right, you will have this time domain feature, right? And you will extract a segment of it, right, to get the amplitude per time, time per amplitude. Wait, amplitude per unit time. And then you will use a Fourier transform to get the power per frequency. And basically you eventually reach to this, which is the, well, you can see the mean frequency per unit time for each segment that you have. And if you're curious what's X, which is the Fourier transform that we just computed, yeah, it's going to be a string of array, yeah. And then we're going to calculate the log amplitude of the STFT to display the spectrogram. Okay. So this is going to be what the spectrogram of the song that we have, simple loop.wave. Right, so basically, how do you read a spectrogram? So you will see that it's frequency per time. That's why we need to calculate it using STFT, right? And the color symbolizes the volume of it or the energy. So you can see that as the frequency increases, it actually dampens a bit. And essentially what a spectrogram is what a waveform. It looks really similar to the waveform that we originally have, right? It's just that the bottom part or the negative aspect of it has been cut off, right? Because of this non-Poynted absolute, right? But it removes the negative values of it so that only the positive values are contained. Right, now let's detect the onset using this function, LeBrossa.onset detect, and we'll calculate the time frame per each onset. So at the 12th segment, there's this 0.27 something seconds per each on that particular onset. Then we'll convert it to sample indices. And then we'll add LeBrossa.clicks, right? So that we add a beep or a click per each onset. And we use IPD.audio again to play the sound. Yep, so that's one beep or click per each onset. And then we're going to segment it to every 100 milliseconds, right? So this is it. So what this does is a list comprehension, right? So for every onset value that we have, right, we actually just use the index slicing, right, to get this 100 millisecond segment. Right, and then what this function actually does is that we're gonna add numpy.zeros, or like just add zeros basically as a padding time, right, which is 300 milliseconds of silence. So because of the zeros that we have, no song at all will be played, right? And then now let's listen to the newly concatenated signal. So you can hear that a lot of like pauses, all because of numpy.0. Now let's extract the features. So we'll compute the zero crossing rate using LeBrossa.core.zero crossing, right? For each segment that we have. Again, it's a list comprehension. So let's print this variable and see what is inside. And then we are going to sort it using the numpy.arg sort. And then let's concatenate it once again. So we're gonna concatenate it by adding that 3 millisecond of silence. And now let's hear what's the difference between when we sort it and versus the original one, which is unsorted. Yeah, so you can hear that the snare drum, or like the highest pitch drum, right? That bang, okay, is played at first for the unsorted one, right? But in here, because we use args.sort, it actually comes towards the last, like the last few seconds of the audio track, right? And I've also had added like 2 more URL links for you to actually use and experiment upon. Right, so far, is there any questions? Right, I'll actually move on to K-means clustering now. I think I'm pretty sure that the previous workshops, you've actually heard of K-means or KNN, and both of them are the most commonly used algorithms, right? And K-means clustering represents an unsupervised algorithm. Meanwhile, KNN is more on the supervised side. And why do we want it to be unsupervised? Basically, we do not have adequate training data in this case, right? And we just want to quickly sort it out relatively against one another. So on just a quick, just a quick look at what K-means algorithm is. So basically, it will take various centroids and then create like a best fit line between these 2 centroids. So that's going to be the boundary between, in this case, 2 classes, yeah. So you can see that one class is red and the other class is classified as yellow. Right. Then it will continue repeating like various combinations, various centroids, right? In this case, it has a new one, right? And then it will continue until it reached to the point whereby there's about an equal number of values in each class, or that it's clearly segregated. So that's what K-means is. And you can see that you don't really need to label the data. It's just that it comparing with one another and relatively to one another, which is the most like preferred way of splitting or classifying these 2 data. Right, so for this case, we'll be using sklearn and MIR eval. Let's import the stuff first. Okay, and let's retrieve audio. So it's a new one, all right, prelude C major. So we'll save it in our machine as classical.a. And in this case, I want to use the simple loop.wave first, which is the drum song that we listened to just now. Like it should have the same sample rate, and the wave plot should look exactly similar. And let's detect onsets. And let's have a beep at each onset. So it should be the same as the previous one, so I'm not going to play it. Now, there's a new one in the feature extraction. So just now we did explore zero crossing rate, but now we are going to explore energy too. So using this function, using function from SciPy. So what energy is, again, is the volume of the audio. And we extract the features for each onset sample. Right, so the next thing is feature scaling, whereby because there's a lot of values at place, you have energy, you have zero crossing rates and all. So what we want to do is to have a fair comparison between them. So we're going to use the min max scalar, right, which is basically just ranging it, like squeezing the value or compressing it such that it's from -1 to 1. Right, so you can see that the minimum value, right, is going to be -1, and the maximum value for both x and y axis is also 1. And then this is us featuring it according to class using plt.scatter. So you can see that, well, you can see that there's like 3 different classes. There's 1, there's 2, and there's like 3. Although the third one on the bottom part is like widely spaced apart, but we'll take it as 1 class. So using k-means, all right, we need to initialize the number of clusters. So as again, I told you that, well, it's roughly 3. So that's why our constant here is going to be 3. Right, and then it will give you a class that's labeled 0, 1, and 2, right? And then we'll use another scatter plot. In this time, we can actually colorize it because we now have various, we now classify it to 3 different classes, right? So you have that, and now we'll actually, wait, let me just run this whole thing. We'll actually play it what each class sounds like. So class 1 is going to be the blue one, which is quite loud in this case, and it has a very low zero crossing rate. Yeah, so it will actually just assign a beat on to class 0. Right, next is class 1, which is the red one, relatively low in volume, and it's sort of the median in the zero in terms of zero crossing rate. Yeah, and then we have class 2, right, which is very loud and it has the highest zero crossing rate. Yeah, I'm not sure whether you can hear the differences. So I'm guessing that class 2 is the kick drum, and class 1 should be the snare drums. Either that or there's something wrong with my ears. Okay, next is affinity propagation, which is another way to cluster the data. And in this case, we do not need to define the number of clusters beforehand. So because we already know that there's about 3 or 2 classes, depending on how you perceive simple loop.wave, right? I think that's sort of pointless to do affinity propagation on that. So this is where classical.wave will be used, right? They have the same sample rate, and then this is what the wave plot looks like. So it's a little bit more messier, and it's quite difficult to detect where's the onset. And then let's detect the onsets again, and then add click at every onset. Yeah, and then let's extract the features, the zero crossing rate and the energy. And then we are gonna scale it again to -1 and 1. So this is what it looks like. Again, it looks roughly like 3, right? So there's 1 at the very top. There's the huge main chunk at the bottom, and there's the tail bits at the end. Right, so let's see what the algorithm actually perceives it to be. Is it also a cluster of 3? So actually we get a cluster of 6 clusters. So from 0, 1, 2, 3, and 4, and 5. And then let's plot the features. Yeah, so this is how the algorithm actually clustered it. You can see that the middle area whereby there's red, purple, blue, and yellow is quite difficult to actually notice the difference between them. So later on, you might not hear the exact difference between class 1, 2, 4, and 0. So this is class 0, which is blue. Yeah, and then class 1 is going to be our red. So quite low energy and relatively okay zero crossing rate. Yeah, so then we'll move on to class 2, which is the yellow one. And because the zero crossing rate is quite high, we can assume that it's quite played often. Yeah, so then moving on to class 3, which is the black one. It's quite loud, but it has lower zero crossing rate. So not that often we should. Yeah, you can hear the beeps or clicks is actually lower than the previous class. And then moving on to class 4, which is in the middle, and it's like going to be very close to the red and the blue classes. Yeah, and last but not least is class 5. That's the most commonly played note, and it's quite soft or low in volume, I would say. Yeah, so I'm not sure whether you can hear the differences correctly because I also can't. All right, now, so far, is there any questions? If not, I'll be moving on to genre recognition. So actually, you don't need pandas. That's like another way of analyzing the data. Okay, so in this case, I do not have the URL links for these two, right? But they are in the drive, and I've already converted them to WAV files. But if you want to venture out on your own, if I'm not mistaken, Librosa doesn't support MP3 or MP4 files. So it only supports .wav files. And I've also have these two references. Either you can convert it to VLC media player, which is most preferred way for those who are using Windows 10, or you can write a Python code for yourself. And for now, we'll be loading the first 30 seconds of Brahms' Hungarian Dance and Busta Rhymes for Days. And then let's play the audio file. And then let's play Booster.
On your mark, get set, ready, go. Let's get them up again. I'm sticking with flows to set another trend. You niggas front like shit ain't for real. Why would you pretend it's bustle back for the kill? Tell a fucking friend before the bomb drop. Hope you good. See when I beat it up with non-stop coke for the hood. The head and heat it up. I'ma leave it up to the street to determine how I lead it up to the nigga head get fucked in the club. I'm about to heat him up.
Been a while since I've seen the light of day.
Okay.
Yeah, so you can see that Brahms is more classical side. Meanwhile, Booster is going to be rap. So let's look at the wave plot features. So you can see that the classical one, yes, it's quite messy, and you can see that there's quite varying frequency being played. Meanwhile, the Booster one or the rapped one, it's quite monotone, or it's quite a single beat. Okay, then let's calculate the Mel spectrogram. We also need to convert the amplitude to decibels. And this is the Mel spectrogram for Brahms. Right, again, it's sort of like very similar to the wave plot that we plotted just now. And the difference between Mel spectrogram and spectrogram is that Mel spectrogram is according to the Mel scale, which is like another way of computing it. But they should be roughly similar. And then this is Booster's one. Okay, so now let's extract each feature, and this is a new one, which is MFCCs. Okay, so which is basing it on the substrum. So what we have right now is this power substrum, right, which is the volume per frequency, right? And then what the function does is that it's going to log it, right, to get the magnitude per frequency. And then it will undergo through another Fourier transform to get the substrum, which is, as you can see, there's like a singular peak here, if we disregard the first peak there. But this singular peak is going to be like the first harmonic, which is the fundamental frequency of the original signal. So you can actually see this singular peak found in the first power spectrum that we have, right? So it's like the fifth peak there. So we'll set the NMFCC as coefficient of 12. And we'll use librosa.features to extract the MFCCs. Right, so let's look at Brahms, the shape of Brahms. And let's look at the mean and the standard deviation of it. So looking at each segment, right, they're quite varying from -200 to -200 to -46 to 37. And then the standard deviation also varies from 62 to 9 to 4. So it's quite really difficult with this like varying degrees of like the long intervals or the gaps between each data or between each computation. So what we're gonna do is, again, we're gonna fit it or scaling feature. All right, in this case, we're gonna use standard scalar, whereby it will have 0 mean and about a univariance of 1. Or like standard deviation of 1. So you can see that the mean it's roughly there. It's definitely a very small value, right? So it's like close to 0. And the standard deviation is about 1. And the next thing is that we're gonna extract the MFCC again for Booster. And then this is going to be the shape. So the shape should be very similar to one another because your feature extraction or the way that you scale it should be the same. Okay, sorry, your feature extraction should be the same. And then now you're going to scale it. You can see that it's not necessarily approximate to 1, but majority of the values do lie within 1. Yeah, and then, sorry, 2 lie within 0 for the mean. And then for the standard deviation, it's roughly close to 1. So let's train the classifier. So we're gonna stack the arrays that we have the scaled values of Brams and Booster vertically wise. And this would be the shape. And then we're gonna concatenate it. This is how we label the data. So 0 is gonna be for Brams and 1 is gonna be for Booster. And just print the shape. Now, we'll create a classifier model using support vector machine. So the support vector machine makes use of a particular parameter called the C parameter. And it basically tells you how much of the data must it be exactly right, like how strict must the boundaries be. Right, so assuming that the white dot is actually our test data, right? And what happens if we have a very high C? So if we have a very high C, right, you can see that it will actually make the best fit line of the boundary, like exactly where the orange area ends and where the blue area ends. Sorry, let me just put it. Sorry for the lag. Let me just refresh my screen. Right, yeah, so because it's exactly where does the orange area and the blue area end, so that's why based on this best fit, the new data is going to be orange, or the test data is going to be orange. So what happens if we have medium C? What is that? Is that it will actually create it somewhere in the middle, right? Whereby we have one orange dot that's outlier. So it's actually neglected. And that's why our white test data is going to be blue because it now lies on the blue boundary that the algorithm has set. And then for the low C, you can expect that it's going to be worse, right? And in this case, there's going to be more outliers that are neglected. So outliers basically means they are abnormal data. And sometimes, depending on what data that you work on, the outliers can actually not necessary, but sometimes they are actually the most important part. Again, it depends on what type of data that you're working on. So in this case, we'll actually set our C constant into 1. But this is basically just the preset, like the default values of it. And then we'll train the classifier. And then we'll run it. So we'll actually, to test it, so that our testing data is going to be the unused 10-second segment from the earlier audio files. So we'll save it as test and xBooster test. Right, so these are the last 10 seconds of the audio file. So that's for Brahms, or the classical one, and then this is for Booster.
Okay. I've been hustling, just cooking in the kitchen, coming up with hits for days. And those involved are black and all.
Which is the rep. Now we're gonna extract the feature again. We're gonna use MFCC for both files. Right, so that's extracting for Brahms, and now we extract for Booster, and they should have the same shape because it's the same feature. And we're gonna transform it again at the same time, like similar size, like 0, mean, and standard deviation of 1. And then we're gonna stack both of them. And we're gonna add the labels. So we're gonna do compute the predicted labels. And then let's compute the accuracy of the score of the data, which is about 97.2%. And now let's predict it. Right, so you can see that this is the predicted label for Brahms. And you can see that majority of it is 0, right? So which is great because based on our labels just now, right? So about 407 of them are zeros. Based on the label just now, 0 is actually a label for Brahms, or the classical music. Right, so basically what this does is that it gets the maximum value of the counts, right, which is 0, right? So majority of the values inside the array is 0, right? And this does, what does is that if you have someone who's not really, because oftentimes your program, you won't tell to the people who use the program, oh, 0 stands for Brahms. So you want a proper output. So this is just having a proper output for it that people who don't know coding can actually understand. Then let's do for Booster rhymes. Right, and you can see that all of the 10 seconds is actually just recognizes it as part of Booster. So of course, so if you run this statement, it would then print the song is rap. So that's all for the MIR and a little bit inside of genre recognition, right? And basically, if you are looking more on music generation, I suggest you can look at Magenta, but that uses command line as compared to Python code. So I'm not sure whether you can actually use it, but it's thus far the most easily one, or it's like easier to understand as compared to other GitHub pages. Yeah, so that would be all for me.
All right, thank you, Rose, for the amazing workshop. I'm sorry, give me a second. Other MC is facing some technical issues. Please give.
Right.
Okay,
Yep. I'm here now.
Okay.
So, since we've ended a bit early for that workshop, you guys now have a win petition session to work on your projects until 3:50. So that's 1 hour and 15 minutes. And do give yourself a little break in between because I know it's been a long day for you guys. So I'll see you guys back at 3:50.
Remember to use the ticketing conference channel if you have any ticketing conference consultation channel if you need any help, and just get some tickets if you need help. Yep. Yeah. Right, I think just about everyone is here. So again, sorry that we cut off your prototype time short for about 5 minutes, but we just have to clarify some things, and it's a miscommunication on our part, so we apologize for that. But here is the rubrics for submission to today. As you can see that, sorry, some groups were asking that they didn't know how to code their prototype. Actually, we are not actually looking for a working code. We are only looking for the usage of AI, the direction of where the team is heading to, whether the prototype shows an intended design or the purpose of the product and the effort. So actually you can do a PowerPoint presentation or other ways to showcase your ideas, and it doesn't have to be code. Of course, if you implement code, we will give you more points for that. But you don't have to implement code if you don't know how to. Second thing is AI bricks. A lot of teams are telling us that they do not know how to use the AI bricks thing. It is fine. Remember, the AI bricks is completely optional and it is up to 200 points. So it is not that if you use AI bricks, you immediately get to 200 points. You get up to 200 points for how well you use AI bricks. Anyway, now we'll be moving on to the next part. Actually, before that, are there any questions regarding the prototype and what you need to submit? If there's any questions, you can put it in the chat right now.
There doesn't seem to be.
Okay, then we shall move on to the next section.
Okay, so you guys will be having your next workshop of the day, which is Dino AI.
Dinosaur? Where?
It's on a slide.
Oh, just the words, not an actual dino. So.
All right. Anyways, let's welcome King and Kingo and Jiayi from Dunman High School.
Thank you. Okay, hi everyone. So I'm Kingo, and joining me today will be Jiayi, who will be bringing through how to build an AI that can play the dinosaur game. And we'll be using this algorithm called NEAT, which stands for Neural Evolutionary of Augmenting Topologies. So our workshop will have two parts. So today is the part one, where we will be basically going through some simple machine learning concepts and also the concepts of NEAT, so you can better understand the coding process. So today will be me and Jiayu doing this presentation. And then, wait, give me a second. Oops, sorry. And then tomorrow will be Isaac and Samuel, who will be bringing you through how to create the dinosaur game itself and how to implement the NEAT algorithm so that we can actually have the AI that can play the game. And yeah, so if you have any questions, do feel free to ask us, and I think we'll try our best to answer any questions that you have. So without further ado, I think Jiayi, you can just begin with the presentation.
Hi everyone, can you hear me? Okay.
Yeah.
So welcome to the section on Introduction to Machine Learning. We'll be going through what is machine learning as well as what is neural network. So the first two sections of our workshop today. of our overall workshop. Yeah. So firstly, today we'll be sharing and introducing to you what machine learning is, followed by the fundamental of how machine learning works, the neural network. So what is machine learning? By definition, it refers to the use of data and algorithm by computer system to imitate the way that human learns, gradually improving its accuracy over time. Machine learning is a subfield in computer science and artificial intelligence that make use of data obtained to make decisions and predictions. Machine learning is increasingly common in our daily lives, and here are some common instances where you can find them being used in. Firstly, in our smartphone, we can use machine learning in facial recognition, as well as when we call Siri, our personal assistants. Machine learning can also be used to help us analyze and predict future trends in stock market. In more professional field, machine learning is used to help doctors detect diseases in early stages based on some common symptoms and signals. So in machine learning, there are three main parts, namely the supervised learning, unsupervised learning, as well as reinforcement learning. Supervised learning refers to when a predefined data is given to train a machine. For example, a set of photos of cats and dogs are given to the machine, and the machine will be guided to find patterns such that they are best able to differentiate cats from dogs. Unsupervised learning, on the other hand, like the name suggests, is unsupervised, which means that the machine will try to seek patterns from the data given without being given any helps, such as saying that, for example, this photo is a cat, that photo is a dog, etc. This will help the machine to find data among the photo and sort them accordingly. Last but not least, we have reinforcement learning, which refers to a method of increasing the efficiency of a machine using a game-like system of rewards and penalties. The machine will try to come up with a solution without any hints from the programmer using try and error methods, where they will either be punished or rewards based on their action, with the aim to make the machine do what the programmer wants in the end. Now that we understand the different categories in machine learning, let's move on to learn more about how the machine works, the neural network. But before that, we have to first understand how the machine learning, the fundamental works too. So unlike classical programming, where you input the data and rules, and the machine will give you the answer, in machine learning, you give the machine both the data and answer, and the machine will try to figure out the logic behind it. Here's a simple example in machine learning. For example, I'll tell the machine that when x equals 2 and when y equals to 10, and when x equals to 7 and y equals to 25, the machine will slowly figure out the algorithm behind it and try to give the algorithm that can give the answer when you input a data. So in this case, the algorithm that the machine is trying to figure out is y equals to 3x plus 4. So in neural network, it's actually inspired and imitated from the human brain neural network. So there are multiple terms that are used in biology that you might find familiar here, but I'll still go through some of them for those that are new to it. So in machine learning, there are firstly the different layers. The first layer is called the input layer, where all the input data are input in. And there are also the output layer, where all the answers will be input also. Then all the data in between will be called the hidden layers. Now let's move on to the individual things in the network. Firstly, all the circles you see in the networks are called the neurons, which helps to store the values of the data. Then afterwards, in between the different neurons, the black lines, they are called a synapse, which helps to connect one neuron to the other neuron. And answer are input in the input. And so since you know that the data and answer are input in the input layers and output layer respectively, what the machine learning is trying to do basically is trying to find the algorithm, or in other words, the connection that help you to change from the input value to your output value. So now that so let's try to understand it with a simple diagram for perceptron. Perceptron is simply a neural network that has only one layer, which means that it doesn't have any hidden layers in between. So there's only the input layer as well as the output layer. So when there are multiple layers, it's called the neural network. But when there's only one layer, it's called the perceptron. And you realize in the diagram shown, there's also W1, W2, and as well as W0 on each black line respectively. And they are called the weights, which help you to change from your input value to your output values. So what does a weight have? And how does it modify to become the algorithm you want? Firstly, in the weight, they are both the weight and the bias, which helps. And to get from the input value to your output value, the weight times your input value, which in this case is your X, will plus the bias will give you your output value, which in this case is your Y. So if you ever already noticed, this is actually your Y equals to mx plus c, where m is the weight and c is the bias. Yeah, so based on the example I gave just now, the m in this case will be 3 and the c is 4. So the weight is 3 and the bias is 4. Now that we understand what the weight is, we will try to understand how the machine learns and adjusts the weight such that it will be able to fit the data that you give. So after for our propagation occurs, which is the process where the weight has been applied to the input value given, the output value will be checked against the expected value that that the programmer will input. Then there'll be a back propagation, which is the process of adjusting the weight. This occurs by changing the weight depending on how different the answer that the machine gets is from the expected answer that the programmer inputs. So this process will repeat for other values also till the machine is able to figure out the algorithm that fits the data and output accurately. And that's the rough overview of how machine learning works. Let's watch a short video to summarize what we just learned.
Last summer, my family and I visited Russia. Even though none of us could read Russian, we did not have any trouble in figuring our way out, all thanks to Google's real-time translation of Russian boards into English. This is just one of the several applications of neural networks. Neural networks form the base of deep learning, a subfield of machine learning where the algorithms are inspired by the structure of the human brain. Neural networks take in data, train themselves to recognize the patterns in this data, and then predict the outputs for a new set of similar data. Let's understand how this is done. Let's construct a neural network that differentiates between a square, circle, and triangle. Neural networks are made up of layers of neurons. These neurons are the core processing units of the network. First, we have the input layer, which receives the input. The output layer predicts our final output. In between exist the hidden layers which perform most of the computations required by our network. Here's an image of a circle. This image is composed of 28 by 28 pixels, which make up for 784 pixels. Each pixel is fed as input to each neuron of the first layer. Neurons of one layer are connected to neurons of the next layer through channels. Each of these channels is assigned a numerical value known as weight. The inputs are multiplied to the corresponding weights, and their sum is sent as input to the neurons in the hidden layer. Each of these neurons is associated with a numerical value called the bias, which is then added to the input sum. This value is then passed through a threshold function called the activation function. The result of the activation function determines if the particular neuron will get activated or not. An activated neuron transmits data to the neurons of the next layer over the channels. In this manner, the data is propagated through the network. This is called forward propagation. In the output layer, the neuron with the highest value fires and determines the output. The values are basically a probability. For example, here, our neuron associated with square has the highest probability. Hence, that's the output predicted by the neural network. Of course, just by a look at it, we know our neural network has made a wrong prediction. But how does the network figure this out? Note that our network is yet to be trained. During this training process, along with the input, our network also has the output fed to it. The predicted output is compared against the actual output to realize the error in prediction. The magnitude of the error indicates how wrong we are, and the sign suggests if our predicted values are higher or lower than expected. The arrows here give an indication of the direction and magnitude of change to reduce the error. This information is then transferred backward through our network. This is known as backpropagation. Now, based on this information, the weights are adjusted. This cycle of forward propagation and backpropagation is iteratively performed with multiple inputs. This process continues until our weights are assigned such that the network can predict the shapes correctly in most of the cases. This brings our training process to an end.
And that's the brief overview of how machine learning works as well as the neural network. Now I'll pass the time to Kingo, which will explain to you how NEAT works theoretically.
Last summer, my family and
Oops, thank you, Jia. Give me a moment now. Okay. Okay, hi everyone. So now we'll be going through the section on NEAT, which is the algorithm that we'll be using to, make our dinosaurs learn how to play the dinosaur game. So NEAT, like the name suggests, stands for Neural Evolution of Augmenting Topologies. NEAT is an evolutionary algorithm that creates artificial neural networks. So yeah, this is NEAT. And then for those of you that do not know what the topology of a neural network is, it refers to the different ways that the neurons are connected. So this kind of just shows you like the two different topologies of a neural network. So just keep this in mind because this is quite important as we move forward. So what are some of the uses of NEAT algorithm? So NEAT can be used for control tasks where you want a specific task to be carried out efficiently and effectively. So in the case of our workshop, it will be to play the dinosaur game well. It can also be used to play many other games such as Flappy Bird or Super Mario. Another area that NEAT can be used for is automated machine learning, which is the process of automating the tasks of applying machine learning to real-world problems, especially for people who do not have the technical data science skills. So one example of this is H2O AutoML, which is designed in such a way that all the users need to do is to point to their data set and tweak a few parameters to train their machine learning model. So the framework. So generally, evolutionary algorithms can be viewed in this framework. So in each generation, they start off with some form of initialization of the population, so which in our case are the dinosaurs. And then these dinosaurs, the population members, will then be evaluated. There might be some form of crossover in the genes, which can be omitted. And finally, the genes will be mutated. So this cycle would then repeat for a given number of iterations until, so this process will then repeat for a given number of iterations, and then the genes will be copied over to the next generations. And okay, I think this probably sounds pretty complicated, but I think the most important thing you need to know right now is what exactly a generation is. So to put it very simply, in the very first generation, you have a bunch of kind of dumb dinosaurs which can barely jump over the obstacle. So after all the dinosaurs in the first generation die out, we then move on to the next generation of dinosaurs, which are smarter and are now able to jump over the first obstacle. So this first generation we call generation 1, and then the next generation we call generation 2. So as the generations gets progressively larger, the dinosaurs will also become smarter and smarter. And thus in generation 100, for example, we have a dinosaur that can play the game way better than any of the dinosaurs in the first generation could. So this is basically how we will get the AI to play the game of dinosaur game well. So I'll now go through some key ideas that you need to know to understand the NEAT algorithm. So these are encoding, crossover, mutation, and speciation. So you see mutation and crossover are in the previous table, which I just mentioned. And yeah, so we start off with the first idea, encoding. So in NEAT, each network architecture has a genotype and a phenotype. Genotype and a phenotype. So if you've taken biology before, you kind of understand that genotypes are like a collection of genes, and then the phenotypes are the observable traits. So in NEAT, right, the genotypes consist of, okay, look at my cursor, okay? So in NEAT, NEAT consists of a node gene and a connection gene set. So the node gene set just contains like the input nodes. So in this case, the sensor, this thing just indicates that it's the input node, the output nodes, and then the hidden nodes. So this is used as a reference when, let's say, these connection nodes find these input and output parameters to construct the connections between the different nodes in the network. And then we go on to connection genes. So each connection gene, this is one connection gene, contains the input value, the input value, the output value, the weight, whether it's enabled or in this case disabled, and then the innovation number. So this innovation number is kind of important, so I'll explain it to you guys now. So an innovation number is kind of like a label, which is permanently assigned to like a newly created connection based on chronological order. So in this case, the connection is from 1 to 4 and it's assigned innovation number 1. So this is a connection. Then 2 to 4 is another connection. 3 to 4 is another connection. So each time the same connection occurs, it will be assigned the innovation number that the first appearance of this connection is assigned to. Okay, so this is kind of confusing, right? So what this means is that, so you know NEAT has many different neural networks, and in each neural network, there will be different connections. So like I mentioned just now, from 1 to 4, this is connection. So, and let's say the first appearance of this neural network, we have a connection from 1 to 4, you'll be assigned innovation number of 1. And because this is based on chronological order, if this connection 1 to 4 occurs again in another neural network, it will be assigned the same innovation number. However, if this connection is completely new, so if you have 2 neural networks and then you have a connection, say from 3 to 5, which is completely new and unseen in any of the neural networks, then it will be given an innovation number based on, well, you'll be given an innovation number based on like the last one, and then you plus 1. So if the last innovation number is like 11, right? And then, so this connection from 3 to 5 will be given like an innovation number of 12. So yeah, so in the diagram, the first connection that occurs, right, is from neuron number 1 to neuron number 4. So if you remember just now, these are the neurons, and this is the synapse, which basically connects the neurons. And then this connection will have an innovation number of 1. So the second connection that occurs, right, is from 2 to 4. So second connection that occurs chronologically. So it has an innovation number of 2, because it's the first time that this 2 to 4 connection occurs. So yeah, and then these innovation numbers, like I mentioned, are also shared across the different neural networks. And well, you might be wondering, so what does that mean? And then why would there be different neural networks? So as mentioned at the very start, right, NEAT is an evolutionary algorithm that creates artificial neural networks. So we go back to this structure, this framework, where we talk about initializing the different dinosaurs in each generation. Okay, so each of these initialized dinosaurs will have their own specific neural network. So one dinosaur will have their own neural network, and another dinosaur with their own neural network. And so that because of this, there will be many different neural networks, and thus you have many different connections between the neurons. So yeah, so when a new connection is created, oops, let me go back. So when a new connection is created, for example, through mutation, which we will cover later, we will first check whether there's already such an existing connection across all the different neural networks. So we go back to 1 to 4 again. So if it exists, then you get the same innovation number because it's not the first unique time that it's occurring. But if not, right, if a new connection that has not occurred across all the different neural networks comes about, you'll be given a new innovation number. And then so which is like I said, you just add 1 to the largest current innovation number. And then these innovation numbers will be kept the same for all the different generations. So that's basically it for innovation numbers and encoding. So now we move on to the next key concept, the crossover of genes. Okay, so we only need to cross over the connection genes. So connection genes are, connection genes are these things, okay? Connection genes. So we only need to cross over connection genes because we can derive the node genes from the connection gene. So in this example, right, we have 2 parents, parent 1 and parent 2, which will, well, in our case, will represent 2 different dinosaurs. So we see parent 1 has 6 connections, 1, 2, 3, 4, 5, 6 connections in the connection gene, and then parent 2 has 9 connections in the connection gene. So you can see that so in this case, right, you can see that parent 2 has 1 more connection than parent 1. So so you see how there's this 6 here, but parent doesn't have a 6 here. So this is the 1 extra connection. So it's 1 extra connection, but a connection from node 2 to 5. So 2 to 5, 2 to 5 has the same innovation number. So these numbers at the top are the innovation numbers that I just mentioned. And then these are the connections. So 2 to 5, 2 to 5. So this is because parent 1 occurs first. You see, so when there's a connection from 2 to 5, it will take the innovation number from parent 1. So, okay, so next thing, so for crossover to happen, right, we first align these parents according to the innovation numbers. So you see how 1 matches with 1 and 5 matches with 5 and so on. Yeah, so for each matching connection gene, right, so this pair, this is called a matching connection. This is called a matching connection gene. So for each matching connection gene, we are going to choose a random connection gene among the 2. So that means we'll choose either this one, this gray one, or this white one. So we'll choose a random one. And then, so the offspring, right? The offspring, which is, well, like the child of these 2 dinosaurs, will have either the connection gene from parent 1 or parent 2. So this offspring has a connection gene from parent 1. And yeah, so excess genes, so these ones at the very end, they are found at the end without a matching connection gene. So if you have genes like this at the end, they are called excess genes. Then destroying genes, in this case, are just genes that do not have a matching counterpart in the other parent, but are not at the end. So in this case, right, if we take out 9 and 10 here, then this destroying gene would be called an excess gene. Yeah. So in this case, right, why do we need to call them excess genes or destroying genes? So, okay, so in this case, right, you see how this offspring takes. So, okay, so when there's destroying genes, sorry, let me talk about this. So when there's destroying genes, right, and which has no matching counterparts, the offspring will just take these destroying genes. So 5 and 6 will be taken by this offspring, and then 8 will be taken. But the excess genes depends on whether parent 1 is fitter or parent 2. So what does being fitter or less fit mean? So fitness in our case, right, means that the dinosaur that can get a higher score. So in our game, right, our goal is to create a dinosaur that can get a very high score. So the further you go, the further you stay alive. You have a fitness score that increments with time. So if you played the dinosaur game before, you know that at the top right corner, there's like sort of like a score counter that increases when you stay alive for longer or when you move further. Yeah, so this is basically the fitness score. So when, in this case, right, how do we choose whether we want to take these activities or not? So in this case, if parent 2 is fitter than parent 1, which means that this parent 2, this dinosaur has a higher score in the dinosaur game than this dinosaur, parent 1, then we will take the excess genes. However, if it turns out that this parent 1, this dinosaur has a higher fitness score, so it plays the game better than this parent 2, then in this case, we will not take the excess genes of parent 2. So if let's say parent 1 is fitter than parent 2, this offspring will not have these 2 genes. So yeah, so that's basically what crossing over means. So in this case, what this means is that parent 2 is more fit than parent 1 because we take the excess genes. Okay, so now let's move on to mutation. So in NEAT, right, mutation can either mutate existing connections or they can add a new structure to the network. So adding a connection is basically just connecting nodes that already exist in the network that do not have a connection. So if you follow my cursor, you see this diagram, you see how 3 and 5 is not connected. So when you add a connection, you basically just connect these 2. Yeah, so that's mutating by adding a connection. So another mutation is to add a node. So in this example, right, we're going to add a new node 6. So this is the original one, this is the new one. So we're going to add a new node 6. So when we add a new node 6, so this works, right? So with a new node 6, node means neurons, okay? Node and neurons is the same thing. So when we add a new neuron, okay, 6, in between this connection, we first disable the connection from 3 to 4. So in the original one, this connection is still enabled, but in the new one, it's disabled. And then we'll have a new connection from 3 to 6, and then 6 to 4. And if you remember from just now, because this connection from 3 to 6 and 6 to 4 are new and unique, that means this connection has not been seen in any other network. So we add them to the back of the connection genes. So you see how it's 8 and 9, 3 to 6. So 3 to 6 occurs first, so it's 8. And then 6 to 4 occurs next, so it's 9. And it's 8 because currently the largest innovation number here is 7. So you can't just give it 7, you have to give it +1 from the largest innovation number. So 8. Yeah. So if let's say in this neural network, right, it has a connection from 3 to 5, then this thing will be in between 6 and 8. So the innovation number 7 will be in between here, and then you have a connection from 3 to 5. So yeah, so that's basically it for mutation. Okay, so now we move on to speciation. So one interesting idea put forth in NEAT, right, was that most new evolutions are not good ones. So just because your dinosaurs like evolve and mutate doesn't really mean that they're actually getting better at the game. Like the score may not reflect. So a jump from generation 1 to 3, right? The generation 3 dinosaurs may not actually have a higher fitness score just because, well, they have more connections or they have mutated. So in fact, right, adding a new connection or neuron, right, which is this, right, adding a node neuron may not actually, before you optimize the weights, right, may often lead to like a lower performing dinosaur. So this right puts new dinosaurs at a disadvantage. So how can we actually protect these new dinosaurs, right, and allow them to optimize? That means allow them to, like, you know, spend some time to get better again before we eliminate them from the population. That means we do not use their neural network for like mutation or mutation or like crossover. So how? So NEAT suggests speciation. So speciation simply splits up the dinosaur population into several species based on the similarity of the topology. So if you don't remember what topology is, it's the different ways the neurons in the neural network are connected. So there's a function for how to decide how to speciate in the documentation. But the important part, right, is that the individuals in a population only have to compete with other individuals in the same species. So what does that mean? So if you look at the diagram on the left, right, you have dinosaurs labeled 1 to 6. Okay, so 1 to 6, these are all dinosaurs. And then these numbers at the right are their fitness scores. So when you speciate, right, you group them according to how similar their neural network is. So you see how 6, so in our case, right, we'll just take that 6 and 2 have a similar neural network. So they're put together as one species. So this is one species. So 3 and 1 has similar neural network, they're one species, and then 5 and 4, same thing, they're one species. So there's 3 species. So when they compete against each other, right, they'll only compete against dinosaurs in the same species. So in this case, it's kind of like a scaled down version, but if we choose, let's say 15 dinosaurs, right, it may not be split equally, like there may be 2 dinosaurs in this species and like 5 here. And yeah, so why do you want to split them into the different species? So this is because of a next process called the selection process, where we can determine how many dinosaurs we want to eliminate, which means removing their topologies. So basically, when we see a dinosaur that, okay, you understand more when we go through the coding process tomorrow, but basically if we have a dinosaur that isn't performing very well, we don't really want to keep their neural network for mutation or crossover because, well, it's not really performing well. So why do we still want to have it like reproduce, right? So, okay, sorry, reproduce as in forming new dinosaurs. Okay, so that means dinosaurs taking their neural network to mutate and crossover. So why do we still want to use these neural networks? So yeah, so when we speciate, we remove the topologies, the neural networks of dinosaurs that aren't performing very well. So in this case, right, we'll remove half of the neural networks of the dinosaurs of each species. So in this case, because the fitness score of 6 of dinosaur 6 is better than dinosaur 2, we'll take out dinosaur. And then 3 better than 1, we'll take out dinosaur 1, and so on. So yeah, so because we speciate, right, we are not only choosing dinosaurs based on how high their fitness scores are. Okay, we are choosing dinosaurs. Okay, sorry. When we speciate, we are still choosing the dinosaurs based on how high their fitness scores are. But dinosaurs with a lower fitness score can still survive until the next generation. So when we speciate, we'll take out 2, 1, 4. But you see how 3 doesn't have a very high fitness score. 70 is not very good, right? And well, 2 is way better than 3, but 2 is eliminated, but 3 isn't. So in this case, right, so if let's say we don't speciate and we just select according to this, so there's no species, all the dinosaurs are put in the same group. The dinosaurs that survive will just be 6, 5, and 2. And then these weaker dinosaurs, we don't have a chance to move on to the next generation. And this, like I mentioned at the very start, may not be very good because, well, dinosaur 3 may have the potential to become good in the future. But because we eliminate it so early, we don't use its neural network in the creation of new dinosaurs. We have no chance to, well, we don't give it the chance to live up to its potential. So yeah, so that's the problem, that we we eliminate these dinosaurs with higher potential before they're able to show their potential. So speciation prevents that. So yeah, so 6, 3, and 5, 3 gets to live even though its score isn't very high. And yeah, so this speciation, right, actually allows the new dinosaurs to be created and optimized without fear that it will be eliminated before it can be truly explored. So we are like letting it live up to its potential. Yeah, so so you see, we'll kill this 3, and then 6, 3, and 5 will continue surviving. And yeah, that's basically it for the concepts of need. Yeah, so if you have any questions, maybe you can just type it on the chat and then we'll try and answer it. Thank you. Oh, so I see a question similar. So, for speciation. So sorry, I try to pronounce your name. Swagat Vikash Saikya asked like, how do you define similar for speciation? Okay, so let me share my screen again. So, okay, oops. So for need, right, for speciation, we talk about splitting the dinosaurs into different species based on the similarity of the topology. So, well, these are the different topologies. So that, well, in need, like I meant, in need, right, they have this function that decides how to speciate. But generally, they just look at your structure, and then if it's similar, you put them in the same group. So in this case, right, this structure is actually kind of similar because it only differs from like one connection. You see, so let's call this, so from this neuron to this neuron, but this one instead of going from this neuron, it goes here. So this is actually kind of similar because every other connection is the same. But if let's say like we remove this connection, right, and then we add a new one. Okay, well, it's kind of hard to show, but let's say we remove this connection and then we connect this neuron to this neuron. Then it's, well, it's kind of different already. So that's like, it can be a new species on its own lah. So basically this function just takes a look at like how different they are and just splits them accordingly lah. Yeah. Yeah, so based on the difference of innovation number list. So yeah, some kind of, yeah. So in this case, well, parent one and parent two, they won't be the same species lah, because their innovation numbers differ. I mean, these connection genes differ by too much. So they will not be put in the same species. Are there any other questions, or are there any parts that we should go through again so you can better understand? You can like text any of us like anonymously if you don't want your question to be seen, or if you don't want your name to be shown. So yeah. Oh, I have one more question. Let me see. So the innovation number list just stores the nodes and connections in each one. In each one, what does each one mean? Sorry. So each neural network, is that what you mean? Yeah, so yes, the innovation number list is for one neural network. Yeah. Okay, last call for questions. If not, then I shall hand it back to Junhong.
All right, thank you, Kingo and Jiayu, for explaining the fundamentals of evolutionary AI as well as how neat works. And I'm sure that all of us can agree that the workshop today was neat, right? Right?
Yes.
Why am I moving backwards? Anyway, now we'll be moving on to the last part, which will be the AI win petition. Once again, you have 1 hour and 15 minutes to continue working on your prototype. Please remember to submit it by 5:45. We will try to give you a feedback for the prototype by 2359 tonight. And if there's any questions, remember to use the ticketing function on Discord. The breakout room should be assigned pretty soon.